No matter whether you are listening tonight from a coastal city, a mountain town, a dry place filled with sunlight, or a region wrapped in rain, the sky above you is never truly still. It may appear empty. It may feel quiet enough to make us think nothing important is happening, but that is only the surface of perception. In reality, air is still moving, heat is still rising, water is still changing phase, and invisible rivers of wind are still flowing thousands of meters overhead. I have always found that to be a beautiful paradox of weather. The most familiar thing is often the easiest to overlook. It taps against windows, cools the skin, wets the pavement, and stirs the leaves. It is so familiar that we almost treat it as the background of everyday life. But if we look a little closer, weather is actually one of the most intricate physical systems on Earth. It is a constant negotiation between sunlight and gravity, between water and the rotation of this planet, between stability and instability. What is remarkable is that this entire mechanism unfolds within an astonishingly thin layer of air. On a planetary scale, the atmosphere is so thin that if Earth were only the size of a classroom globe, the surrounding air would be thinner than a coat of varnish covering its surface. And it is precisely this fragility that makes everything more unforgettable. How can such a thin layer of gas carry the power of enormous swirling storms? Why does rain pour down in one place while a town only a few kilometers away remains dry? And why, even with satellites, radar, and supercomputers, has the sky never stopped surprising us? Weather is not meaningless chaos. It is not random in the way we sometimes imagine. It operates with remarkable consistency under clear physical laws: the ideal gas law, the laws of thermodynamics, the conservation of energy, and the influence of Earth's rotation through the Coriolis effect. These ideas do not remain still inside textbooks. They are present in the clouds above your head. The wind sliding past your window tonight may have begun with sunlight heating the equatorial regions several days ago. The rain falling on your roof may be carrying energy released when water vapor condensed high in the troposphere. And a storm forming out over the ocean may be drawing its strength from heat the sea has been quietly storing for months. If it must be said very simply, weather is motion. It is energy redistributing itself. It is a state of imbalance, constantly seeking balance again. But what makes the atmosphere both powerful and remarkable is that it is also extremely sensitive. A small shift in temperature, a slight difference in humidity, or a minor disturbance in pressure can grow into thunderstorms, blizzards, or heat waves. The atmosphere knows how to amplify, how to organize itself, and how to evolve from very small initial differences. Perhaps that is why there is something humbling about looking up at the sky. Every place that listeners mention in the comments, from deserts and rainforests to city skylines and quiet rural fields, is not as separate as it might seem. All of it belongs to the same planetary system. Air circulates through enormous global patterns, through Hadley, Ferrel, and polar cells that connect the equator to the poles. High above, jet streams ripple like invisible rivers. Lower down, the oceans absorb and release heat in cycles, helping shape the rhythm of the seasons. In weather, nothing truly exists in isolation. Even as these opening words are being spoken, somewhere in the world sunlight is warming the dark surface of the ocean. Somewhere, warm air is rising. Somewhere else, cold air is sinking. Tiny droplets of water are forming around microscopic particles of dust. And in yet another place, a region of low pressure is beginning to rotate. The sky is always moving, even when our eyes cannot see it. Understanding weather does not really begin with memorizing symbols or charts. It begins with something much simpler, recognizing that the atmosphere is a physical system governed by pressure, temperature, density, humidity, and motion. Everything begins with energy. From there, patterns gradually emerge. Convection forms. Winds align themselves. Water evaporates and condenses. Storms organize into spirals. Fronts collide, and jet streams shift. All of it follows principles that can be described clearly and calmly. And yet, weather still retains a certain strangeness of its own. Invisible air carries vast oceans of water vapor. Heat high above, where humans cannot directly feel it, can determine storms far below. A planet rotating steadily in space can quietly bend the winds in ways both subtle and powerful. The sky tonight may look peaceful, but it is not still. It is not passive. It is a system in motion, changing continuously, powered by the sun and shaped by Earth's rotation. So whether you are listening beneath a sky full of stars, beneath drifting clouds, beneath distant thunder, or beneath steady rain, the same physical story is unfolding above you. And through this slow journey, the invisible machinery of the atmosphere will gradually reveal itself, not through haste, not through drama, but through careful and patient observation. There is something memorable about weather. It does not operate by magic, it operates by physics. And once those quiet mechanisms begin to reveal themselves, even a gentle breeze no longer feels ordinary. Step outside on a calm evening and look up, and it is easy to feel that the sky is something vast, almost endless, stretching from one horizon to another, fading from blue into gold and then into darkness. Yet what creates clouds, wind, rain, and storms in that seemingly boundless space actually exists within an astonishingly thin layer of air. Earth's atmosphere is only a fragile shell of gas surrounding a rocky planet. If the entire planet were reduced to the size of a classroom globe, the region of the atmosphere where almost all weather occurs would be no thicker than a coat of paint covering its surface. That is not poetic exaggeration. It is simply a matter of scale. Inside that thin shell, the main component is nitrogen, which makes up about 78% of the air by volume. Oxygen accounts for about 21%. The remaining 1% is a mixture of argon, carbon dioxide, neon, helium, methane, and trace amounts of other gases. Water vapor, although its concentration varies greatly from nearly zero in cold polar air to several percent in humid tropical air, plays a role far larger than its small proportion might suggest. Each of these components plays a different role. Nitrogen, under normal atmospheric conditions, is largely inert and forms a stable background. Oxygen supports respiration and combustion. Argon is chemically quiet and mainly present simply as a gas occupying space. Carbon dioxide is different. Even though it exists in only a tiny fraction of a percent, it can absorb and emit infrared radiation, influencing Earth's temperature through the greenhouse effect. But if one component must be considered the most dynamic, it is water vapor. It changes phase easily, carrying energy away during evaporation and releasing energy again when it condenses. We often feel that air is almost weightless. In reality, it has mass, and anything with mass is influenced by gravity. Gravity pulls the air toward Earth's surface, and from this the phenomenon of atmospheric pressure emerges, the force produced by the weight of the air above pressing down on a point below. At sea level, the average pressure is about 101,000 pascals. This can be imagined as the weight of a column of air extending through the entire atmosphere, gently pressing down on every square meter of the surface. The atmosphere maintains this condition through a very important balance, hydrostatic equilibrium. I have always found this idea both simple and elegant. On one side, gravity pulls gas molecules downward. On the other, the pressure gradient force pushes upward. When these two forces balance, the atmosphere does not collapse entirely to the ground, but it also does not drift away into space. Instead, it forms a stable structure in which air gradually becomes thinner with height. The higher you go, the lower the pressure becomes. Density also decreases. Within the same volume, there are fewer and fewer gas molecules. At the summit of Mount Everest, atmospheric pressure is only about 1/3 of what it is at sea level. This change does not happen abruptly. It occurs smoothly and continuously, forming a density gradient that extends upward for hundreds of kilometers. To better describe this gaseous shell, scientists divide the atmosphere into several layers based on how temperature changes with altitude. Closest to the surface is the troposphere. Above it lies the stratosphere. Higher still are the mesosphere, the thermosphere, and finally the exosphere. where the atmosphere gradually fades into space. Almost all of the weather we experience in everyday life occurs within the troposphere. This layer begins at the ground and extends upward to an average of about 12 kilometers, though that number is not fixed. Near the equator, it may reach about 17 kilometers. Near the poles, it may be only about 8 kilometers thick. Within the troposphere, temperature generally decreases with altitude at a rate commonly known as the environmental lapse rate, about 6.5 degrees Celsius per kilometer under typical conditions. That decrease in temperature with height is a fundamental detail. It is what allows warm air near the surface to rise. It is precisely because temperature decreases with altitude that warm air can rise, and in many cases the water vapor within it condenses into clouds. If that thermal structure did not exist, the entire vertical motion that drives weather would be profoundly different. And just above the region where thunderclouds form lies a very different world, the stratosphere. There, temperature no longer continues to fall but instead begins to increase with height, mainly because ozone molecules absorb ultraviolet radiation. This temperature distribution creates a temperature inversion that suppresses vertical mixing. Perhaps that is why this layer is far more stable, so stable that clouds and storms rarely reach it, and also one of the reasons commercial aircraft often cruise near its lower boundary. Higher layers, such as the mesosphere and thermosphere, experience extremely high temperatures and strong interactions with radiation from the sun. But in everyday life, they rarely directly control the rain or sunshine we experience. The true engine of weather still lies within the troposphere. In this lower layer of air, the atmosphere is never still. Temperature differences create pressure differences. Pressure differences push air into motion as wind. Water vapor condenses into tiny droplets. Those droplets combine into clouds. Energy is absorbed, transported, and released again. If weather had to be reduced to a single idea, it would be the redistribution of energy through the motion of air and water. All of this motion is not arbitrary. It follows fundamental principles of physics. The behavior of gases can be described by the ideal gas law. Pressure, multiplied by volume, equals the number of moles multiplied by the gas constant and temperature. Even setting the equation aside, the essence of it is quite intuitive. When air is heated, its molecules move faster, the air mass expands, its density decreases, and it begins to rise. When air cools, the molecules slow down, the air mass contracts, becomes denser, and sinks. This simple relationship between temperature, pressure, and density supports the entire mechanism of convection, the vertical motion that builds clouds and powers storms. Gravity ensures that air that rises will eventually cool and slow down. Meanwhile, the pressure gradient force causes air to move from regions of higher pressure toward regions of lower pressure. When these influences combine, they produce larger patterns that we recognize as winds, atmospheric fronts, or circulation cells. The atmosphere is not chaotic in the sense of being lawless. On the contrary, it has structure, it responds to change, and it obeys thermodynamics, fluid dynamics, and the conservation of energy with remarkable consistency. Imagine a quiet summer afternoon. The ground absorbs sunlight and gradually warms. The layer of air just above the surface warms as well, expands, and begins to rise. As it climbs higher, the surrounding pressure decreases. The air parcel therefore expands further, and this expansion cools it through a process called adiabatic cooling. Cooling that occurs when an air mass expands without exchanging heat with its surroundings. If that rising air cools to its dew point, water vapor condenses into countless tiny droplets, and a cloud is born. This entire process is simply the atmosphere responding to uneven heating. For that reason, weather always begins with imbalance. The equator receives more solar energy than the poles. Land warms faster than the ocean. Dark surfaces absorb more energy than bright ones. From these differences, temperature gradients form. Temperature gradients create pressure gradients. Pressure gradients generate motion, and motion transports energy from place to place. Even the gentlest breeze is part of this process. A cloud drifting across the sky is actually the visible trace of invisible thermodynamics. And a distant storm is simply a large-scale expression of the same principles that lifted a pocket of warm air from a sunlit stretch of road. What has always made the sky seem both beautiful and formidable to me is that such a thin atmosphere contains an enormous amount of energy. A fully developed thunderstorm, over its lifetime, can release an amount of energy comparable to several atomic bombs, not through a sudden explosion, but through the steady release of latent heat when water vapor condenses. And that energy, if traced back to its origin, was absorbed from sunlight during the earlier stage when water evaporated. The sky is therefore not passive, it is always active, constantly adjusting itself like a living fluid system. Understanding this thin layer of air, maintained in hydrostatic equilibrium, a layer held by gravity and shaped by temperature gradients, is the foundation for understanding everything that follows. Without that fragile shell, there would be no clouds, no rain, no wind, and nothing we call weather. Life on Earth depends deeply on this delicate balance. The atmosphere blocks harmful ultraviolet radiation, softens temperature extremes, provides oxygen for respiration and carbon dioxide for photosynthesis, and carries water across continents. All of this happens within a layer of matter that, on a planetary scale, is almost unimaginably thin. Yet the energy inside that thin layer does not arise on its own. Far above, beyond the clouds, beyond the jet streams, even beyond the faint upper reaches of the thermosphere, there is a steady and persistent source of energy radiating in every direction. The sunday. It does not burn like a flame on Earth. Its energy comes from nuclear fusion. In the sun's core, where temperatures reach about 15 million degrees Celsius and pressure becomes almost unimaginable, hydrogen nuclei collide and merge. In a star the size of the Sun, the dominant process is the proton-proton chain. Step by step, hydrogen is transformed into helium. Along the way, a very small portion of mass is converted into energy. That idea is tied to Einstein's principle of mass-energy equivalence. Energy equals mass, multiplied by the square of the speed of light. Because the speed of light is so large, even a tiny amount of lost mass can produce an enormous amount of energy. Every second, the Sun converts hundreds of millions of tons of hydrogen into helium, and several million tons of that mass are transformed directly into radiation. That energy travels outward from the core, passes through the dense interior layers, and eventually leaves the Sun's surface as electromagnetic radiation. Visible light, infrared radiation, ultraviolet radiation, and a small fraction of other wavelengths. Only a tiny portion of that radiation reaches Earth. The average amount of solar energy striking the top of the atmosphere on a surface facing directly toward the Sun is called the solar constant, about 1,360 watts per square meter. It is not perfectly constant. Solar activity causes slight variations, and agencies such as NASA and ESA monitor these changes closely. But for the purpose of understanding weather, that input is stable enough to be treated as a nearly steady stream of energy. When this radiation arrives at Earth, it is called insolation incoming solar radiation. This stream of energy does not fall evenly across the planet. Because Earth is spherical, regions near the equator receive more direct sunlight than the poles. Near the equator, sunlight arrives at a steeper angle, concentrating energy over a smaller area. Near the poles, sunlight arrives at a lower angle, spreading the same energy across a much larger surface. As a result, tropical regions receive significantly more energy per unit area than polar regions. And Earth's axial tilt, about 23.5 degrees relative to its orbital plane around the Sun, adds another layer of difference. This tilt is what produces the seasons. When one hemisphere tilts toward the Sun, it experiences longer days and more direct sunlight. 6 months later, the situation reverses. Thus, the spherical shape of Earth and the tilt of its axis alone ensure that solar heating is always uneven, both in space and in time. Yet even the energy that arrives is not all absorbed. Some of it is reflected back into space. The degree of this reflection is called albedo. Bright surfaces have high albedo, while dark surfaces have low albedo. Fresh snow can reflect up to 80, even 90% of incoming light. The ice sheets of Antarctica and Greenland are also highly reflective. In contrast, the dark surface of the ocean absorbs most of the light that reaches it and reflects only a small portion. Forests absorb more energy than deserts. And from these differences, the larger story of weather continues to unfold. Not every surface on Earth responds to sunlight in the same way. The pale sand of a desert reflects more light than dense vegetation, though it still does not reflect as strongly as fresh snow. And these seemingly simple differences actually matter a great deal. A place that reflects most of the incoming light will remain cooler. A place that absorbs most of the sun's radiation will warm more quickly and more efficiently. The clearest example is the ocean. Covering about 70% of the planet's surface, it has a relatively low albedo but a high heat capacity, which allows it to absorb enormous amounts of energy and then release that energy very slowly. Land behaves differently, especially in dry regions, warming quickly and cooling much faster. NASA's Earth science satellites, including the clouds and the Earth's Radiant Energy System program, closely track the amount of solar energy entering the atmosphere, as well as the portion that is reflected or radiated back into space. From these measurements, scientists monitor the planet's energy balance. On average, Earth absorbs nearly as much energy as it emits. But even a slight shift in that balance will eventually cause global temperatures to adjust over time. For weather, however, the key point is not that average balance. The key point is that heat is not distributed evenly. The equator receives more energy than it loses, while the poles lose more than they receive. This creates a temperature gradient stretching from low latitudes to high latitudes. And anywhere there is a temperature gradient, there is already the seed of motion. Warm air expands and becomes less dense. Cold air contracts and becomes denser. As a result, where air is warmer and lighter, surface pressure is usually lower. Where air is cooler and denser, pressure is usually higher. These pressure differences do not appear randomly. They arise directly from uneven heating. Nature always tends toward balance. The excess energy in the equatorial regions must be transported toward the poles, and both the atmosphere and the oceans share that task. In the atmosphere, this redistribution happens through large-scale circulation patterns. Warm air rises near the equator, drifts poleward at high altitudes, cools, and eventually sinks. That is part of the Hadley cell circulation. If we step back far enough, we can see that the deepest cause of this entire circulation system is not wind, it is sunlight. Even small changes in the input of solar energy can leave clearly visible marks. During the day, land under direct sunlight warms up, creating local pressure differences large enough to generate sea breezes and land breezes along coastlines. Over longer timescales, the seasonal variation in incoming solar radiation shifts entire monsoon systems, shaping rainfall patterns that sustain billions of people. Every one of these processes, if traced back to its deepest origin, begins with nuclear fusion in the sun's core. The scale of this story is so vast that it is easy to underestimate. The sun's total power output is about 4 times 10 to the 26 watts. Only a tiny fraction of that energy reaches Earth. Yet even that small portion is enough to drive global wind systems, evaporate enormous quantities of water, and sustain life. Every cloud exists because of evaporation powered by sunlight. Every wind follows the trail of temperature differences created by solar radiation. Even the violent spirals of tropical cyclones are drawing their strength from ocean water warmed by months of accumulated sunlight. If that stream of energy were to stop, Earth's atmosphere would cool and become more stable. Winds would weaken, the hydrologic cycle would slow down, and weather as we know it today would gradually settle into a long, quiet state. But that does not happen. The sun continues to shine steadily. Energy continues to reach the top of the atmosphere. Some of it is reflected back by clouds and ice. Some is absorbed by land and sea. Some warms the air directly. Some drives evaporation. Some feeds convection. And it is this steady flow of energy that creates imbalance. And imbalance creates motion. So the story of weather does not really begin with rain or wind. It begins with light crossing space. A photon born in the sun's core may take thousands of years to escape to the surface, bouncing continuously among particles in the dense interior. But once it escapes into space, it needs only a little more than 8 minutes to reach Earth. Just over 8 minutes after leaving the sun, that very same packet of energy may be warming a patch of ocean, heating a stretch of desert, or falling onto leaves in a forest. And from that moment on, the atmosphere begins to respond. If we stand still for a moment on a windy day, the motion of air can seem very simple. Wind brushes past the skin, shakes the leaves, and pushes clouds across the sky. It feels almost playful, as if the air simply wants to wander. But air does not move on impulse. It moves because of physics. And at the center of that motion is thermodynamics, the branch of physics that describes how heat and energy behave. Air is a mixture of gases, which means it is a crowd of molecules in constant motion. They collide with one another, with surfaces, and with everything they encounter. Temperature, at its most basic level, is simply a measure of the average kinetic energy of those molecules. When air warms, the molecules move faster. When air cools, they slow down. That difference alone is enough to change the behavior of an entire mass of air. When heated, the molecules in air move slightly farther apart. The air mass expands. If it is free to move, that expansion reduces its density. Density is simply the amount of mass contained in a given volume. Less dense air is lighter per unit volume than denser air. And because denser air contains more mass, gravity acts on it more strongly. So when a mass of air becomes warmer and lighter than the air around it, it begins to experience buoyancy. This is the same principle that allows a hot air balloon to rise. The warm air inside is lighter than the cooler air outside, so it floats upward. In the atmosphere, this upward motion is called convection. Convection begins with Earth's surface being heated unevenly. Sunlight warms a strip of land. The layer of air directly above that strip warms as well. As it heats up, it expands, becomes lighter than the surrounding air, and begins to rise. As that column of air rises, cooler air from the surrounding area flows in to replace it. That horizontal motion toward the rising column is the beginning of wind. Cooler air, being denser, tends to sink. As it sinks, it increases pressure near the ground. By contrast, where air is rising, surface pressure decreases. These pressure differences are not vague. They can be measured, and they are the direct cause of wind. Air always moves from areas of high pressure to areas of low pressure under the influence of the pressure gradient force. Put simply, a pressure gradient is a change in pressure over distance. If two nearby locations have different pressures, then a gradient exists between them. The pressure gradient force pushes air from higher pressure toward lower pressure. The greater the pressure difference across the same distance, the stronger that force becomes, and the stronger the wind becomes as a result. To see clearly why differences in temperature can create differences in pressure, we can return to the ideal gas law. In words, it says that pressure multiplied by volume equals the number of gas particles multiplied by the gas constant and by temperature. This relationship tightly links pressure, temperature, density, and volume. If temperature increases while the number of gas particles remains the same, then either pressure must increase or volume must increase. In the open atmosphere, air can expand vertically, so when it is heated, it usually responds by expanding upward rather than by sharply increasing pressure at the surface. And in that process, its density decreases. Cooler air does the opposite. It contracts and becomes denser. Denser air near the surface contributes to higher surface pressure. Warm rising air contributes to lower pressure. Even very small differences like these are enough to set the atmosphere in motion. A difference of just a few millibars between two regions is already a measurable imbalance in the weight of the air columns above them. And sometimes, from a small difference like that alone, the sky begins to move. The atmosphere always responds with the same physical instinct. It tries to move toward equilibrium. Air moves because that equilibrium has been disturbed. Today, that may sound obvious, but recognizing that air actually has weight, was once a major turning point in the history of science. In 1643, the Italian scientist Evangelista Torricelli carried out a simple but profound experiment. He filled a glass tube with mercury and then inverted that tube into a dish of mercury. Some of the mercury remained suspended inside the tube. What mattered was that it was not being sucked upward, as many people at the time believed, but was being supported by the pressure of the air pushing down on the surface of the dish below. From that moment on, the barometer was born. The height of the mercury column changed with atmospheric pressure, and for the first time, people could directly measure the force of the air. That became the foundation of modern meteorology. Without pressure measurements, there could be no reliable forecasting, no maps of high and low pressure systems, and no numerical understanding of wind. When the barometer falls, it is often a sign that pressure is dropping, that air is rising, and that unsettled weather is approaching. When the barometer rises, it usually suggests the opposite: sinking air and a tendency toward more stable skies. Behind those changes on the dial lies a very strong relationship between temperature, density, and pressure. Warm air, once it begins to rise, cannot remain in the same state forever. The higher it goes, the lower the surrounding pressure becomes. Lower pressure allows the rising air parcel to expand, and that expansion requires energy. That energy is drawn from the parcel's own internal energy, causing it to cool. When this cooling happens without any exchange of heat with the surrounding air, it is called adiabatic cooling. If the parcel continues to cool to a low enough temperature, the water vapor inside it condenses into tiny droplets, and clouds begin to form. What is interesting is that condensation does not only create clouds, it also releases latent heat, returning some energy to the rising air parcel. In some cases, that heat helps it rise even higher. That is one of the reasons thunderstorms can grow into such tall and powerful structures. But if we trace the process all the way back to its first cause, the entire story still begins with a very simple temperature difference. Air moves because it is trying to reduce an imbalance. Heat creates density differences. Density differences create pressure differences, and pressure differences create motion. That motion does not happen only in the vertical direction. As soon as air begins to flow horizontally from areas of high pressure toward areas of low pressure, other forces begin to affect its path. Earth's rotation creates the Coriolis effect, causing moving air to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. What matters to remember, however, is that the Coriolis effect is not the starting point. It only acts on air that is already moving because of a pressure gradient. The original cause is always uneven heating. If we think of the atmosphere as a fluid, everything becomes more coherent. It flows and accelerates according to the principles of fluid dynamics, described mathematically by the Navier-Stokes equations. Although the full form of those equations is very complex, the core idea is simple. A fluid accelerates when a force acts on it. In the atmosphere, the large-scale force that initiates that motion is the pressure gradient force. So even a light breeze touching your skin at ground level is part of an ongoing adjustment between warm and cool regions. Warmer places tend to produce rising motion and lower pressure. Cooler places tend to produce sinking motion and higher pressure. Air flows between those regions in response to the difference. Even on a clear day with light winds, countless small convection cells may still be quietly forming and fading away. Above an overheated road, shimmering air rises. Over a shaded grassy field, cooler air sinks. Those very small motions are not meaningless. They combine into larger patterns. No drama is needed here. The physics of the sky is steady and consistent. Air moves because temperature differences exist. Those differences appear because sunlight is not distributed evenly, and the laws of gases ensure that differences in temperature become differences in density and pressure. From a few such fundamental principles, the sky's endless motion is born. A mass of warm air rising from sunlit ground may seem like something very local, a wavering shimmer above asphalt, a gentle breeze along the coast. But when that process is expanded across thousands of kilometers, the atmosphere begins to reveal a very different level of organization. It does not circulate in random, scattered swirls. It organizes itself into broad, semi-stable circulation systems that stretch across entire hemispheres. Two major causes lie behind that structure. The equator always receives more energy than the poles, and Earth is rotating. Let us begin at the equator. Here, sunlight arrives more directly than anywhere else on the planet, so the air near the surface warms strongly, becomes lighter, and rises. That persistent upward motion creates a belt of relatively low pressure encircling Earth. But air cannot keep rising forever. As it rises, it cools through adiabatic expansion. At high altitude in the troposphere, it begins to spread gradually toward higher latitudes. This branch of air that rises and then flows poleward forms the upper part of a circulation loop called the Hadley cell, named after George Hadley, the 18th century English scientist who proposed an early model of tropical circulation. In that model, air rises near the equator, flows poleward aloft, cools, then sinks around 30 degrees latitude, and finally returns toward the equator near the surface. It is around 30 degrees north and south, where the air sinks, that surface pressure increases. Many of those regions are associated with the world's great deserts, such as the Sahara and the Australian interior. As air sinks, it is compressed and warms, which makes cloud formation less likely. The result is that clear skies and dry conditions often dominate. From those subtropical high-pressure regions, air flows back toward the equator along the surface, but it does not move in a straight line. Because Earth rotates from west to east, any moving body of air experiences an apparent deflection due to the Coriolis effect. Gaspard Gustave de Coriolis described this effect mathematically in 1835 while studying rotating systems. In the atmosphere, that influence causes air to veer to the right in the northern hemisphere and to the left in the southern hemisphere. It does not create the wind, but it bends the path of air that is already moving because of pressure differences. So when surface air flows from the subtropical highs back toward the equatorial low-pressure belt, it is deflected westward. This produces the trade winds. The northeast trades in the northern hemisphere and the southeast trades in the southern hemisphere. For centuries, these steady winds carried sailing ships across the Atlantic and the Pacific. But the Hadley cell is only one part of the overall circulation system. Between about 30 and 60 degrees latitude lies another circulation loop, the Ferrel cell, named after the American meteorologist William Ferrel. Unlike the Hadley cell, which is driven mainly by strong heating at the equator, the Ferrel cell is more complex and is shaped by interactions between tropical and polar air masses. In this mid-latitude zone, surface air generally flows from the subtropical highs toward lower pressure regions near 60 degrees latitude. Once again, the Coriolis effect alters its path. In the northern hemisphere, air moving poleward is deflected eastward, producing the prevailing westerlies. These westerlies dominate much of the weather pattern over North America, Europe, and parts of Asia. Many storm systems in those regions move from west to east because they are steered by those winds. Around 60 degrees latitude, where warmer air from the Ferrel cell meets colder air descending from the polar regions, a boundary zone rich in instability forms. This is where storms often develop and where weather changes frequently. Farther toward the poles, the polar cell completes the trio of major circulation loops. Over the poles, very cold, dense air sinks, creating high surface pressure. From there, air flows equatorward along the ground. As it moves, it continues to be deflected westward by the Coriolis effect, forming the polar easterlies. These winds are often weaker and more variable than the trade winds or the prevailing westerlies, but they still help shape polar weather. The three large circulation loops, Hadley, Ferrel, and polar, together form the three-cell model of the atmosphere in each hemisphere. Of course, reality is more complex than this simplified picture, but as a conceptual framework, it is extremely powerful because it shows how energy is transported from the equator toward the poles. And right at the equator, where the two Hadley cells meet, there exists a region of special importance, the intertropical convergence zone. Near the equator, there is a particularly important atmospheric zone, often abbreviated as the ITCZ. It is a belt of low pressure where the trade winds from the two hemispheres meet. When they converge, the air has no choice but to be forced upward, and once that air mass begins to rise, it gradually cools. The water vapor inside it begins to condense. Towering cumulonimbus clouds can grow very high, and heavy rain, thunderstorms, and deep convection become familiar features of the region. The ITCZ does not stay fixed in place. It shifts northward or drifts southward with the seasons, following the region that receives the most solar energy. That migration helps shape the monsoons and rainfall across vast areas of Africa, South America, and South Asia. This convergence zone is sometimes also called the doldrums, because surface winds there can be quite weak, especially when vertical motion dominates. In the age of sailing ships, it was once a place where vessels could become trapped on calm seas while dramatic towering storm clouds rose overhead. And although the three-cell model of atmospheric circulation is a powerful framework for understanding the planet, it is not a rigid structure. It still shifts with the seasons, with ocean temperatures, and with long-term climate variations. Even so, its overall form remains clear enough for meteorologists to recognize and monitor. Today, those observations are coordinated on a global scale by organizations such as the World Meteorological Organization. Satellites observe the movement of clouds, temperature gradients, and wind speeds, while weather balloons are launched every day from many locations around the world to measure atmospheric conditions at different altitudes. When all of that data is combined, people gain a moving picture of planetary circulation. At high altitudes, near the boundaries between circulation cells, narrow bands of very fast winds form the jet streams. They arise in part because of strong temperature contrasts between air masses and are shaped by the Coriolis effect, becoming atmospheric rivers that guide storm systems across continents. If we look far enough, everything still leads back to the same deepest cause. The equator receives more energy than the poles. The atmosphere responds by trying to move that excess heat elsewhere. Warm air rises, drifts poleward, gradually cools, sinks, and then returns. That cycle repeats continuously. So although individual storms may look very chaotic, the large-scale structure of atmospheric circulation is surprisingly orderly. Thermodynamics, fluid dynamics, and the rotation of the planet all take part in that process at the same time. A breeze in the mid-latitudes may carry within it the trace of sinking air from the Hadley cell thousands of kilometers away. A storm crossing the North Atlantic may be following a path laid out by the prevailing westerlies of the Ferrel cell, and rainfall in equatorial regions may depend directly on where the ITCZ happens to be that year. To look at the sky on a planetary scale is to see enormous circulation loops linking deserts with rainforests, linking the polar regions with tropical seas. Air moves not only because it is warm or cold, but because Earth is a rotating sphere receiving sunlight unevenly. From that comes a structured circulation system, connecting local winds to global flows. But even though temperature differences alone are enough to make air move, without water the weather would be far quieter. In a way, water is the atmosphere's quiet amplifier. It is present in the oceans, lakes, rivers, soil, and even on the surfaces of leaves. When sunlight warms these surfaces, some water molecules gain enough energy to leave the liquid phase and enter the air as vapor. That is evaporation. This process requires energy, and that energy is taken from the surrounding environment, causing the surface to cool slightly as water changes from liquid to gas. But evaporation is only one part of an unending cycle. Water vapor rises with warm air. At higher levels, when the air mass cools, that vapor may condense into liquid droplets or freeze into ice crystals. When the droplets or ice particles grow large enough, they fall as rain, snow, sleet, or hail. Once water reaches the ground, it may run off, seep downward into groundwater, or return to the ocean. This entire exchange between the surface and the atmosphere is the water cycle. At first glance, this cycle may seem simple, but hidden within those phase changes is an enormous source of energy. When water evaporates, it absorbs heat from the environment, without increasing its own temperature at that moment. That energy is stored in the molecular bonds of water vapor and is called latent heat. The word latent is exactly right, because that energy does not yet appear as temperature. It is carried invisibly within the vapor. When the vapor later condenses back into liquid droplets, that stored energy is released into the surrounding air as heat. This can warm rising air masses, making them even more buoyant and allowing them to continue rising higher than they would have without condensation. The scale of this energy is not small. Evaporating 1 kilogram of water under typical atmospheric conditions requires about 2 million joules. That is enough to power a small electric heater for several minutes. If we multiply that number by the amount of water evaporating each day from the tropical oceans, we begin to see how vast this engine really is. Put simply, evaporation stores solar energy in water vapor, and condensation releases it later, often at higher altitudes. This mechanism lies at the center of storm development. A thunderstorm growing over warm ocean water does not draw its strength only from the hot air below. It is actually being fed by latent heat, released as water vapor condenses inside the rising cloud towers. That energy continues to fuel upward motion and deepen the storm. If water vapor were removed from the atmosphere, circulation would still exist, winds would still blow, because pressure differences would still exist, but storms would be weaker, temperature contrasts would be less intense, and the sky would be much quieter. That is why humidity cannot be ignored when trying to understand weather. Humidity is simply the amount of water vapor in the air, but it can be described in several ways. Absolute humidity is the actual mass of water vapor in a given volume of air. In meteorology, the more familiar measure is relative humidity, which describes how close the air is to saturation. In other words, it is the ratio between the amount of water vapor actually present and the maximum amount the air can hold at that temperature, expressed as a percentage. There is a very important point here. Warm air can hold more water vapor than cold air. This relationship is described by the Clausius-Clapeyron relation, which shows that the saturation vapor pressure of water increases as temperature rises. In practical terms, for about every 10 degrees Celsius of warming, the maximum amount of water vapor that air can hold increases significantly. When relative humidity reaches 100%, the air is saturated. If the air then cools further or receives more water vapor, condensation begins. The temperature at which air reaches saturation is called the dew point. When air cools to the dew point, tiny droplets begin to form. Dew on grass during a cool morning is a familiar example. The grass surface cools below the dew point of the surrounding air. In the sky, the same principle works in the same way, only on a much larger scale, as rising air cools to its dew point and forms clouds. Humidity does not only affect how weather feels, it also directly affects how the atmosphere behaves. When humidity is high, sweat evaporates more slowly from the skin, making hot conditions feel even more oppressive. When humidity is low, evaporation happens more quickly, creating a cooler sensation even when the temperature is not low. But beyond bodily experience, humidity is also deeply tied to atmospheric stability. Moist air rising does not cool in the same way as dry air, because during condensation, latent heat is released and offsets part of the cooling. This means that moist air, under some conditions, can be more buoyant than dry air. This difference is described by the moist adiabatic lapse rate, which is smaller than the dry adiabatic lapse rate. When meteorology began to move beyond the stage of merely recording what could be seen and heard and entered the world of systems of equations, one of the people who saw that direction most clearly was Wilhelm Bjerknes. In the late 19th and early 20th centuries, this Norwegian scientist recognized that to truly understand weather, thermodynamics could not be separated from fluid dynamics. The atmosphere, in his view, had to be treated as a complete physical system, in which motion, heat transfer, and moisture were tightly linked, and all obeyed mathematical laws together. That idea laid the foundation for dynamic meteorology, where weather was no longer seen as a collection of scattered observations, but as the result of physical laws interacting at the same time. In that picture, water vapor was not a supporting detail. Bjerknes understood that very clearly. Moisture affects air density, affects energy, and affects pressure patterns as well. So if one wants to forecast weather, it is not enough to know how the wind is blowing or how temperature is changing. One must also account for humidity and every phase change of water. When water vapor condenses in a rising air mass, latent heat is released into the surrounding environment. That can lower surface pressure even further, strengthen the pressure gradient, and make winds stronger. In tropical cyclones, this process appears on a very clear scale. Warm ocean water provides continuous evaporation. Moist air spirals into the storm's center and rises, and there, an enormous amount of latent heat is released in the storm's core, causing central pressure to fall even more and the rotating circulation to spin faster. Water vapor does not start atmospheric motion by itself. That opening role still belongs to uneven heating and the pressure gradients it creates. But water vapor makes the consequences of motion much greater. It deepens low-pressure systems, feeds convection, and determines where precipitation will occur. Even in cold climates, moisture does not retreat. Snowstorms form when moist air is lifted and then cools below the freezing point. Ice crystals grow around microscopic particles and eventually fall as snow. The principles of latent heat remain fully at work there as well, except that the phase changes may include freezing in addition to simple condensation. Most of the water vapor in the atmosphere comes from the oceans, and the tropics, with their highest sea surface temperatures, supply especially large amounts of it. From there, winds carry moisture across continents. Rainforests live on these transport pathways. Mountain ranges block the path of moist air and force it upward, producing orographic rainfall. Water therefore becomes the bridge between land and sky, in an exchange that never stops. If water vapor were removed from Earth's atmosphere, this planet would look much more like Mars, dry, thin, with few clouds, and almost no precipitation. But on Earth, because water is abundant and temperatures are moderate enough, water can exist at the same time in all three forms: solid, liquid, and gas. That ability is what gives weather its richness. Whenever a cloud appears, it marks the moment when energy once stored during evaporation is being released. Whenever rain falls, part of that energy journey has completed another stage through the atmosphere. So moisture does not merely accompany weather, it makes weather stronger. Air moves because there are pressure gradients created by uneven heating. But when that air mass is also carrying water vapor, it is carrying energy that has already been stored. When the vapor condenses, that energy is released, supporting upward motion and sometimes turning a gentle convective region into a towering storm structure. The sky's most spectacular displays often carry their power from something invisible: water-changing phase. Even on a calm day, humidity quietly determines when clouds begin to form, how tall they can grow, and how much energy they may release. It is the boundary between invisible vapor and visible cloud. Water, in ordinary life, feels too familiar to notice. But in the atmosphere, it is a powerful amplifier, turning sunlight into motion and then turning that motion into weather. Looking at a cloud from the ground, it is easy to feel that it is almost within reach, like a solid object with shape, edges, texture, casting shadows on the ground, glowing gold at sunset and blushing pink at dawn. But a cloud is not solid at all. It is only countless tiny droplets of water or tiny ice crystals suspended in the air, so small and light that they can float for a very long time before falling. A cloud is born when invisible water vapor becomes something the eye can see. For that to happen, air must cool to its dew point, the temperature at which it becomes saturated and begins to condense. When air rises, it expands because it enters a region of lower pressure, and that expansion is what cools it through an adiabatic process. The energy required for that expansion is taken from the air mass's own internal heat, so the temperature drops without any exchange of heat with the surrounding environment. Once the dew point is reached, water vapor molecules begin to gather together. However, in the real atmosphere, they almost never form droplets entirely out of nothing. Most condensation requires a surface to cling to, and that surface comes from condensation nuclei. These nuclei are extremely tiny, solid or liquid particles suspended in the air. Dust from dry ground, sea salt thrown up by breaking waves, soot from combustion, pollen from plants, or sulfate particles produced by volcanoes. Even in air that seems very clear, billions of such invisible aerosol particles are still present. Water vapor is drawn toward them, clings to their surfaces, and forms the first droplets. Without these condensation nuclei, clouds would require much higher humidity to appear, and the sky would probably be far less cloudy. As condensation continues, the droplets grow larger. But even in a typical cloud, water droplets are usually only about 10 micrometers across, far smaller than raindrops. A raindrop must be about 100 times larger in diameter before gravity can overcome the upward motions keeping it suspended. So a cloud is the visible sign that air has cooled enough to reach saturation. It marks the place where motion and thermodynamics meet. Air can be lifted to the point of condensation in several different ways. One of the most familiar mechanisms is convective lifting. When the sun heats one patch of ground more than the surrounding area, the air above it also warms, becomes buoyant, and begins to rise. If, as it rises, it cools to the dew point, cumulus clouds may appear, those familiar puffy clouds with flat bases and rounded tops, often seen on warm afternoons. Another mechanism is orographic lifting. When moist air encounters a mountain range, it cannot move through the rock, so it is forced to climb the slope. In the process, it cools. Clouds form on the windward side, and rain or snow often follows. On the leeward side, the air descends, warms, and dries out, producing a rain shadow effect. There is also frontal lifting. When two air masses of different temperatures meet, warm air is usually forced to rise. Along a cold front, denser cold air wedges underneath and lifts warm air rapidly. Along a warm front, warm air gradually slides up over the cooler air mass. Though the details differ, all of these lifting mechanisms follow the same basic principle. Rising air cools, and if it cools enough, it can reach saturation and form clouds. People began trying to name different cloud forms quite early. The classification system widely used today traces back to the work of Luke Howard, an English chemist and amateur meteorologist. In 1802, he introduced a structured naming system based on Latin, creating a consistent language for describing the sky. Cumulus means heap or mass, and cumulus clouds do indeed look like separate cottony lumps with clear edges, often showing localized convection. Stratus means layer. Stratus clouds spread out in broad gray sheets, covering large portions of the sky, and sometimes bringing light drizzle or a lingering gloomy feeling. Cirrus means curl or lock of hair. Cirrus clouds are very high, made mostly of ice crystals, thin and wispy like drawn-out streaks, often signaling changes taking place in the higher atmosphere. And then there is cumulonimbus, where the heap nature of cumulus meets the rain-bearing character of nimbus. These are towering thunderstorm clouds that can rise beyond 10 kilometers, sometimes reaching the lower stratosphere. Inside them, powerful updrafts and downdrafts collide, twist, and interact, producing heavy rain, lightning, hail, and in some cases even tornadoes. From the outside, they may appear to be only a huge, dark mass of cloud, but seen through the lens of physics, they are the place where water, heat, and motion meet at their greatest intensity. The names of cloud types can sometimes sound soft and almost poetic, but behind them lie very specific physical differences. High clouds such as cirrus exist in the cold region of the upper troposphere, where temperatures have already fallen far below freezing. Lower down are the middle-level clouds, such as altostratus and altocumulus. Closer to the ground still are the low clouds, such as stratus and nimbus. They do not simply make the sky look less empty. Each type of cloud is revealing something about how the atmosphere is operating. A line of cumulus clouds growing over a sun-heated field shows that convection is active. A widespread layer of stratus may reveal broad uplift along a frontal boundary, and thin streaks of cirrus racing high overhead are often a sign of very strong winds in the upper troposphere, usually associated with jet streams. The cloud base does not appear at a random height. It forms at the altitude where the rising air mass cools to its dew point. That height can often be estimated simply by looking at the difference between the surface temperature and the dew point temperature. If that difference is small, it usually points to a low cloud base and moist air. If the difference is larger, the air is drier, and clouds will form at a higher altitude. But the role of clouds does not stop at revealing humidity or vertical motion. They also participate directly in Earth's energy balance. Low, thick clouds reflect a large portion of incoming solar radiation, increasing the planet's albedo and helping cool the surface. High, thin cirrus clouds do the opposite. They can trap outgoing infrared radiation and contribute to warming. The way these two roles affect climate feedback is still an active area of research. What is interesting is that although clouds look so obvious, they are actually mostly empty space. Even a thick cloud may contain only a few grams of liquid water per cubic meter. What makes us see it is not that it is dense in the sense of containing a great deal of matter, but that the countless tiny droplets inside it are scattering sunlight. In a way I have always liked, a cloud is the place where invisible thermodynamic processes suddenly take on a visible shape. When air rises and cools, clouds appear. When air sinks and warms, the tiny droplets evaporate back into water vapor, and the clouds disappear. The sky becomes clear again, but the physics behind it has never stopped. A cloud drifting overhead is therefore like a sign drawn across the sky, where air is rising, where moisture is condensing, where latent heat is being released. It allows us to see vertical motion that is normally invisible. There are days when the sky seems very balanced. Clouds drift lazily, the air rises gently and then sinks again. Nothing violent happens. But under a slightly different set of conditions, that same sky can erupt into towering thunderstorms, lightning, and torrential rain. The boundary between these two states lies in atmospheric instability. Instability is the tendency of an air parcel to continue rising once it has been lifted. The clearest way to understand this is to compare the rising parcel with the surrounding environment at the same altitude. If the parcel remains warmer than its surroundings, it is lighter, more buoyant, and will continue to rise on its own. If it is colder than the surrounding air, it loses buoyancy and sinks back down. The key comparison here is the rate at which temperature decreases with height. In the surrounding atmosphere, this rate is called the environmental lapse rate, averaging about 6.5 degrees Celsius per kilometer in the troposphere, though in reality it varies from place to place and from day to day. A dry air parcel rising upward cools faster. According to the dry adiabatic lapse rate, about 10 degrees Celsius per kilometer. If the parcel is moist and condensation has already begun, its cooling slows because latent heat is being returned to it. This slower rate is the moist adiabatic lapse rate, usually around 5 to 7 degrees Celsius per kilometer, depending on temperature and humidity. From here, instability becomes very easy to see. If the temperature of the surrounding environment decreases with height faster than the rising parcel cools, then that parcel can remain warmer than the environment throughout its upward journey. Once that happens, buoyancy increases and the upward motion begins to accelerate on its own. But if the surrounding atmosphere cools too slowly with height, the rising parcel will soon become colder than the environment and be pulled back down. That is a stable state. Even small changes in the slope of the temperature gradient are enough to determine whether the sky will remain quiet or develop into a storm. To quantify this buoyant energy, meteorologists use a measure called CAPE, or convective available potential energy. It indicates how much buoyant energy an air parcel can gain if it is lifted through an unstable layer of the atmosphere. CAPE is measured in joules per kilogram. On quiet days, its value may be nearly zero, but on days with strong thunderstorm potential, It can reach thousands of joules per kilogram. The larger the value, the greater the chance of strong updrafts. CAPE, however, is only potential. It does not turn into a storm by itself. A triggering mechanism is still needed to lift the air to the height where buoyancy can take over. That mechanism may be surface heating, a frontal boundary, or terrain forcing the air upslope. When warm, moist air near the ground begins to rise through convection, the first stage of a thunderstorm begins, the cumulus stage. The rising air cools, reaches saturation, and a cumulus cloud forms. If instability is weak, that cloud will develop only slightly and then dissipate. But if the atmosphere is strongly supportive, the updraft does not stop. Condensation inside the cloud releases latent heat, and that heat makes the parcel even more buoyant. The updraft is strengthened. The cloud grows rapidly upward and may reach 10 to 15 kilometers in height. When it reaches the upper troposphere, the cloud top spreads outward and forms the characteristic anvil shape of a cumulonimbus cloud. That is the mature stage of the thunderstorm. Inside the cloud, strong updrafts lift droplets and ice particles high into the sky, while precipitation has already begun. When raindrops or ice particles become heavy enough, they fall. As they fall, they drag air downward with them, creating downdrafts. At that point, the storm becomes a true dynamic system, where air is continually rising and sinking within the same structure. In the upper part of the cloud, collisions between ice particles create charge separation. Positive and negative charges gather in different regions, and when the electrical potential difference becomes large enough, lightning appears to rebalance the imbalance. Thunder is the sound of air expanding suddenly after being intensely heated by the lightning channel. Then comes the point when downdrafts begin to dominate. Cold air spreads out across the surface, cutting off the supply of warm, moist air that had been feeding the storm. The updraft weakens, the structure collapses, and the thunderstorm dissipates. For a simple thunderstorm, that entire life cycle may last less than an hour, but more complex systems can survive much longer. Research from the National Severe Storms Laboratory in the United States shows that only very small differences in temperature, humidity, or wind shear can determine whether an ordinary thunderstorm will fade away or develop into a violent system. Wind shear, meaning a change in wind speed or direction with height, can tilt and organize updrafts, allowing downdrafts to fall away from the storm's main fuel source instead of cutting it off directly. Under the right conditions, this leads to a supercell, a type of storm capable of producing large hail, destructive winds, and tornadoes. What is truly remarkable is that sometimes only a very small difference, just a few degrees of temperature or a modest change in humidity, is enough to push the atmosphere from a gentle state into a violent one. That sensitivity exists because buoyancy depends directly on the temperature difference between the air parcel and the surrounding environment. A parcel only 1 or 2 degrees warmer than the surrounding air, if the environment is unstable enough, can accelerate upward very rapidly. And once latent heat from condensation enters the process, that small initial difference can be amplified into a powerful updraft. Weather systems do not operate in a simple linear way, where a small cause produces only a small result. They are nonlinear systems. Because of that, a very slight difference in the initial conditions can sometimes open the way to an outcome far larger than intuition would suggest. A small increase in surface temperature can significantly change CAPE. A moderate shift in wind shear can alter the storm's structure completely. From a very weak temperature gradient near the ground, the sky can still develop into a cumulonimbus tower reaching the edge of the stratosphere. This is not an exception to physics. It is exactly how physics behaves when conditions allow amplification to occur. The energy of a thunderstorm, in the end, still comes from solar heating and the latent heat stored in water vapor. Instability does not create new energy. It only determines how efficiently that energy is converted into motion. So instability itself does not always mean danger. It is only potential. There are many days when the atmosphere already contains that potential, but no trigger is strong enough to unlock it. and so the sky remains clear, even though the energy is there. But when a rising air mass reaches that reservoir of potential, everything can accelerate very quickly. The updraft strengthens, the cloud deepens, electric charges begin to separate, and the rain grows heavier. Still, air can turn into violent motion because the atmosphere is a fluid system that is especially sensitive to gradients of temperature and humidity. The same thermodynamic principles that can lift a small cumulus cloud from the ground can, under more strongly unstable conditions, create a violent storm. To understand instability is to understand why the sky can shift from a gentle blue to a thunderous gray so quickly. Air moves because of pressure differences. It rises because of buoyancy. It accelerates because of instability. And when that upward motion begins to take on rotation, the atmosphere enters a far more complex level of organization. Over warm ocean water, when air rises strongly and surface pressure begins to fall, a very subtle but very powerful process can begin. Air from the surrounding area rushes toward the low-pressure center. If Earth did not rotate, that air would flow straight inward. But this planet is rotating from west to east, and so any moving current of air is bent by the Coriolis effect. In the northern hemisphere, air flowing toward a low-pressure region is deflected to the right. In the southern hemisphere, it is deflected to the left. As a result, instead of moving straight inward, the wind begins to spiral around the low-pressure center. In the northern hemisphere, the inflowing wind spirals inward counterclockwise. In the southern hemisphere, it spirals inward clockwise. This kind of organized rotation around a low-pressure center is called cyclonic circulation. The word cyclone, in its most basic sense, simply refers to a storm system rotating around a region of low pressure. It does not by itself say whether the storm is weak or strong. It describes the structure, not the intensity. And in that structure, air spiraling into the center does not pile up there. It is forced to rise. As it rises, it cools, water vapor condenses, and latent heat is released. That heat makes the air column above the storm's center warmer, which lowers surface pressure even further. The lower the pressure falls, the stronger the pressure gradient becomes. The stronger the pressure gradient, the faster the winds accelerate. Stronger winds then pull even more converging air into the center. A feedback loop begins to form. When this feedback loop becomes well organized over sufficiently warm ocean water, a tropical cyclone can be born. Its name changes depending on the region. In the Atlantic and the northeastern Pacific, it is called a hurricane. In the northwestern Pacific, it is called a typhoon. And in the Indian Ocean and many parts of the South Pacific, it is usually called simply a cyclone. But beneath those geographic names, the physics is exactly the same. For a tropical cyclone to form, the sea surface usually must first reach about 26 to 27 degrees Celsius, and not just in a thin surface layer but through a sufficiently deep layer of water. Warm water is the energy source through evaporation, and the deeper that warm layer is, the more durable the supply becomes. The second condition is that the atmosphere above must be unstable enough to support deep convection. Rising air must be able to keep rising without being blocked by stable layers. The third condition is that vertical wind shear must be relatively weak. If the winds aloft are much stronger than, or too differently oriented from, the winds near the sea surface, they can tilt or tear apart the convection trying to organize, preventing the system from developing in a vertically aligned structure. And finally, an initial disturbance is usually still needed, such as a tropical wave, a weak, low-pressure disturbance moving westward through the tropics to provide the initial convergence and spin. When these conditions come together, clusters of thunderstorms begin to gather around a central low-pressure area. Latent heat continues to be released in the convective core. Pressure in the center falls more deeply. Air rushes inward faster, and the Coriolis effect causes that inflow to spiral more and more tightly. Gradually, an eye may appear at the center of the storm. The eye is a relatively calm and less cloudy region, formed because air in the storm's core rises strongly in a surrounding ring called the eye wall, while in the exact center, air sinks more gently. Around the eye wall is where the strongest winds and heaviest rain occur. As the pressure gradient tightens, wind speed increases, and the storm becomes a highly organized energy system, drawing heat from the warm ocean surface and converting it into the kinetic energy of wind and the potential energy of rising air masses. To classify hurricanes, the Saffir-Simpson wind scale is commonly used, based on sustained wind speed. A Category 1 storm begins at 74 miles per hour, and the scale rises to Category 5 for storms with sustained winds above 157 miles per hour. However, this scale does not directly measure rainfall or storm surge, even though those hazards often accompany powerful storms. In the United States, the National Hurricane Center under NOAA tracks tropical cyclones in the Atlantic and Eastern Pacific using satellites, reconnaissance aircraft, offshore buoys, and computer models. Similar agencies do the same work in other ocean basins around the world. Although they can cause tremendous destruction, tropical cyclones are not mysterious phenomena when viewed through the lens of thermodynamics. They function like heat engines. Warm, moist air rises and releases latent heat. Around the edges, cooler air sinks. The entire system is doing something very specific, transporting heat from the ocean surface upward and outward. The maximum theoretical intensity such a storm can reach depends in part on sea surface temperature and the structure of the atmosphere above it. Put simply, the greater the temperature difference between the warm ocean surface and the colder upper atmosphere, the greater the available convective potential. A mature tropical cyclone can release energy at a rate equivalent to several hundred times the total electrical generating capacity of the entire world, although most of that energy exists as latent heat rather than as energy humans could use directly. Strong winds are only one part of that enormous total energy flow. As long as the storm remains over warm water and wind shear stays weak, it can maintain or even increase its intensity. But when it moves over colder water or makes landfall, its energy supply begins to decline. Friction with the land disrupts the circulation. Without continuous evaporation to feed the system, the storm gradually weakens. Even so, cyclonic rotation is not unique to the tropics. Low-pressure systems in the mid-latitudes rotate as well, though their structure is different. If tropical cyclones are fueled mainly by latent heat and energy from warm ocean surfaces, then mid-latitude cyclones depend much more on horizontal temperature contrasts between air masses. Even though they are organized differently, the underlying principle does not change. A low-pressure area pulls air inward. Earth's rotation bends that airflow. Rising motion at the center helps sustain the system, and the energy released by condensation further reinforces the pressure fall. In other words, rotation does not create motion out of nothing. It gives motion a form. If Earth did not rotate, a low-pressure system would be much simpler. Air would simply rush into the center, rise, and spread outward. But because this planet rotates, that motion is no longer straight. It bends, then gradually organizes itself into spiral paths. Rain bands begin to wrap around the center. Winds strengthen along curved trajectories. And the storm, instead of being a chaotic flow of air, becomes a structured system. Seen from space, a tropical cyclone carries an almost striking symmetry. Broad cloud bands curving gently around the eye at the center, so beautiful they can seem almost graceful. But beneath that symmetry is violent motion, fueled by the continuous exchange of energy between the ocean and the atmosphere. Large rotating storms are not disorganized explosions. They are the atmosphere's structured response to imbalances of heat and pressure, the way the sky tries to redistribute energy on a planetary scale. As those rotating systems move poleward, they no longer exist in the same environment. They encounter different temperature gradients, run into different circulation patterns, and from that, new kinds of cyclones begin to appear. In the mid-latitudes, the origin of storms no longer lies only in warm oceans, but also in the contrast between warm and cold air masses stretching across entire continents. That is why weather in temperate regions often feels so changeable. A sunny morning can give way to rain by the same afternoon. A mild day can be replaced by noticeably colder air overnight. These shifts are often far from random. Behind them are boundaries in the atmosphere called fronts. A front is a transition zone between two air masses of different temperatures and often different humidity as well. An air mass is a large body of air with relatively uniform thermal and moisture characteristics throughout its extent. Some air masses develop over cold land, while others form over warm oceans. When they move and meet, the boundary between them becomes a front. If a colder, denser air mass advances into a warm air mass, a cold front forms. Because it is heavier, the cold air wedges underneath the warm air and forces it upward. That lifting can happen very quickly. Warm air lifted along a cold front often cools rapidly, condenses intensely, and produces narrow but severe bands of rain. Thunderstorms commonly develop along strong cold fronts, especially in spring and summer. After the front passes, temperatures usually drop, winds shift direction, and the sky often clears again. A warm front is different. Here, a warm air mass moves toward a colder one. Because it is lighter, it cannot easily shove the colder air off the surface. Instead, it gradually glides up over it in a process called overrunning. This type of lifting is much broader and gentler than along a cold front. As a result, warm fronts are often accompanied by layered clouds such as altostratus or nimbostratus, producing steady precipitation over wide areas, with temperatures gradually rising as the front passes. And when neither air mass is strong enough to force the other to retreat significantly, the front becomes nearly stationary. This is called a stationary front. Clouds and rain can then linger along this boundary, sometimes producing a prolonged rainy spell. Later, in the life cycle of a mid-latitude storm, the cold front may catch up to the warm front. When that happens, the warm air that had once lain between them is lifted completely off the ground, and an occluded front forms. From that point on, the surface system becomes increasingly dominated by cold air, and the storm usually begins to weaken. A systematic understanding of these fronts was clarified in the early 20th century by the Bergen School in Norway. Under the influence of Wilhelm Bjerknes and his colleagues, that school developed the polar front theory. The core idea was that mid-latitude storms form along the boundary separating cold polar air from warmer subtropical air, the polar front. Along that boundary, a small disturbance can cause warm air to move poleward on one side while cold air surges equatorward on the other. From such a wave, a cyclonic circulation can develop. As the system grows, the cold front and warm front become more distinct. Eventually, the cold front catches up to the warm front, creating an occlusion and leading the system into its decaying stage. To this day, this conceptual model remains a foundation of modern meteorology. What makes extratropical cyclones different from tropical cyclones is their energy source. Tropical cyclones depend mainly on warm oceans and the release of latent heat. Extratropical cyclones, by contrast, feed on horizontal temperature contrasts between air masses. This state is called baroclinicity. Along the polar front, where the temperature gradient is especially strong, the atmosphere stores potential energy. When a disturbance appears, that potential energy can be converted into kinetic energy. Winds strengthen, and the low-pressure center deepens. Such systems can span thousands of kilometers. On satellite images, they often have a comma-shaped appearance. Within the same system, many different kinds of weather may occur. Heavy snow on the cold side, rain along the warm front, thunderstorms along the cold front, and clearing skies behind it. Unlike tropical cyclones, which weaken when they leave warm oceans, extratropical cyclones can often intensify over land. Because they depend more on the contrast between cold continental air and warmer oceanic or subtropical air, season has a very clear influence here. Winter brings a greater temperature contrast between the equator and the poles. Continental cold air masses become stronger, the polar front sharpens, and those gradients allow mid-latitude storms to develop more violently. Some winter storms deepen so rapidly that meteorologists call the process explosive cyclogenesis, a very sharp drop in central pressure within just 24 hours. In summer, When temperature contrasts in the mid-latitudes are generally weaker, the most intense extratropical cyclones are less common, but that does not mean the sky becomes simple. Local convection and frontal interactions can still produce significant weather. The preferred paths of these storms usually follow the prevailing westerlies. These winds steer storm systems from west to east across North America, Europe, and parts of Asia. For that reason, coastal regions in those areas often experience repeated frontal passages. In everyday life in temperate climates, many familiar weather signs are really just near-surface expressions of those frontal interactions. Thickening clouds through the day may signal an approaching warm front. A sudden gust of wind accompanied by a sharp band of dark cloud may be a cold front. A wind shift together with falling barometric pressure may suggest a nearby developing low-pressure system. In the end, everything still returns to the same familiar physical principles. Temperature differences create density differences. Density differences create pressure gradients. And pressure gradients produce wind along frontal boundaries, where those differences are especially pronounced. So, extratropical cyclones are not random spirals of cloud on satellite images. They are organized systems, born from temperature contrasts spread across large regions, then converting the potential energy stored along the polar front into motion and weather. Even when the sky looks calm, the boundary between air masses may still be shifting quietly somewhere overhead. The interaction between warm and cold air remains central to mid-latitude weather. And above all of those surface systems, there exists yet another layer of atmospheric structure where extremely fast winds race along the planet and determine the path and intensity of storms. At high altitudes, far above the cloud layers that bring rain and snow, there are narrow but powerful bands of wind racing around Earth. These are the jet streams. A jet stream is a relatively narrow but very fast current of air located in the upper part of the troposphere, usually near the boundary with the stratosphere. Wind speeds within it often exceed 100 kilometers per hour and can sometimes surpass 300 kilometers per hour. Compared with commercial aircraft, these are speeds that in some cases can even exceed the ground speed of many flights when they are strongly assisted by a tailwind. And the origin of these jet streams, in the end, still begins with something familiar: very strong horizontal temperature gradients in the atmosphere. High in the atmosphere, where the eye cannot directly see the invisible boundaries of temperature, the contrast between warm and cold air masses begins to leave its mark on the structure of pressure. Especially along the polar front, where temperature differences are strong, pressure surfaces aloft are not perfectly horizontal but become tilted. Warm air expands vertically more than cold air, so at the same altitude, pressure is often higher over warm regions and lower over cold ones. From this, strong pressure gradients emerge in the upper atmosphere. Air responds to these gradients by accelerating, but because the atmosphere rotates with Earth, the Coriolis effect continually bends that motion. When the pressure, gradient force, and the Coriolis effect reach a balance, the wind no longer cuts across isobars but flows almost parallel to them. Meteorologists call this geostrophic flow. From that balance emerges a very distinctive structure: narrow but extremely strong bands of wind, stretching almost west to east. These are the jet streams. The strongest and most persistent jet is the polar jet stream, usually found near latitude 60 degrees in both hemispheres. There is also the subtropical jet stream, located closer to about 30 degrees, associated with the descending branch of the Hadley cell. These jets are not fixed throughout the year. In winter, when the temperature contrast between the equator and the poles is stronger, the polar jet is often intensified. In summer, when that contrast weakens, the jet stream also tends to weaken. But what makes them truly interesting is that they do not flow in straight lines. They meander in vast waves stretching thousands of kilometers. These oscillations are called Rossby waves, named after Carl Gustav Rossby, who described their dynamics in the 1930s. The origin of these waves is linked to the conservation of potential vorticity in a rotating fluid. When air moves northward or southward, the Coriolis parameter changes with latitude. To maintain its dynamical consistency, the flow adjusts by forming very large-scale waves. Where the jet stream bends poleward, Meteorologists call it a ridge. Where it dips toward the equator, it forms a trough. Beneath ridges, conditions often favor high pressure, relatively calm weather, and warmer air. Beneath troughs, low pressure and atmospheric instability are more likely to develop. The position of the jet stream can therefore determine the paths of storms. Many extratropical cyclones tend to form or intensify beneath jet stream troughs, where divergence aloft supports rising motion below. In that sense, the jet stream acts like a steering current, quietly guiding storm systems across continents. Even a small shift in its position can significantly change weather at the surface. If the jet stream shifts northward, a region may fall beneath a persistent ridge and experience several days of warm, dry conditions. If it dips southward, cold air from higher latitudes may plunge much farther south than usual, bringing unusual cold spells. Sometimes Rossby waves become very large and move slowly. When that happens, the atmosphere can enter a blocked state. A blocking pattern occurs when a high-pressure ridge becomes nearly stationary, interrupting the usual west-to-east progression of weather systems. The consequences of such a pattern can persist for quite some time: heat waves, droughts, or prolonged rainfall. For that reason, variations in the jet stream are often mentioned when analyzing extreme weather events. A very deep trough can allow frigid polar air to slide far southward and trigger severe cold outbreaks. Conversely, a strong ridge can trap hot air in place and contribute to extended heat waves. There is still ongoing research into how changes in Arctic temperatures may influence the behavior of the jet stream. Some studies suggest that declining sea ice and warming in the Arctic may weaken the temperature gradient between polar and mid-latitude regions, potentially altering the jet stream's pattern. However, this remains an active area of investigation. Even though it lies high above the ground, the jet stream has clear effects on conditions below. The timing of frontal passages, the strength of storms, and even the distribution of rainfall often bear the imprint of upper-level winds. Pilots understand this very well. Eastbound flights across the Atlantic can shorten travel time by riding strong tailwinds within the jet stream, while westbound flights often take longer because they must fight against it. The jet stream is not a single, unchanging river of air. It is a constantly shifting band, sometimes stronger, sometimes weaker, sometimes more meandering, reflecting the evolving state of the atmosphere. It represents a delicate balance between temperature gradients, Earth's rotation, and pressure patterns aloft. From the ground, it is invisible. There is no clear line in the sky that one can point to and say the jet stream is there. Yet sometimes its presence can be sensed in fast-moving streaks of cirrus clouds or in the way storm systems race across weather maps. At altitudes of around 10 kilometers, these rivers of air are quietly guiding rain, clear skies, warmth, and cold below. And while the upper atmosphere performs that steering role, beneath it lies another system just as powerful: the ocean. We often think of weather as something that happens only in the air: clouds gathering overhead, winds sweeping across fields, rain falling from the sky. But beneath many of those motions lies a vast reservoir of energy, deeper and far more patient. The ocean covers about 70% of Earth's surface, and it is not merely the backdrop for the drama of the sky. It is an active participant. The first reason lies in a fundamental property of water: its high specific heat capacity. Water can absorb large amounts of energy without its temperature changing very quickly. As a result, compared with land, ocean water warms more slowly during the day and cools more slowly at night. Over longer timescales, such as through the seasons, this difference becomes even clearer. A sandy beach can heat rapidly under the afternoon sun and cool just as quickly after sunset. But the adjacent ocean surface changes temperature far more gradually. Water molecules can store and redistribute energy efficiently through molecular motion and mixing within the water column. For the same increase in temperature, water requires far more energy than dry soil or rock. For that reason, the oceans become an enormous heat reservoir for the planet. In the tropics and subtropics, the oceans absorb vast amounts of solar energy. Some of that heat returns to the atmosphere through evaporation and sensible heat transfer. Another portion is carried toward higher latitudes by ocean currents. This stored heat helps moderate coastal climates, which is why regions near the sea often experience smaller seasonal temperature ranges than inland areas at the same latitude. But moderating temperature extremes is only part of the ocean's role. In certain regions, interactions between the ocean and atmosphere create major patterns of climate variability that can influence weather across entire continents. One of the most important of these patterns is ENSO, the El Niño Southern Oscillation. This is a cyclical variation in sea surface temperatures and pressure patterns across the equatorial Pacific. Under normal conditions, trade winds blow from east to west along the equator, pushing warm surface water toward the western Pacific near Indonesia and Australia. This allows cold, nutrient-rich water to upwell near the west coast of South America. But during an El Niño event, the trade winds weaken. Warm surface water begins to spread eastward across the central and eastern Pacific. Sea surface temperatures in those regions rise above average, and when the ocean changes in that way, the atmosphere changes with it. Patterns of convection shift, and rainfall that normally concentrates over the western Pacific can gradually migrate eastward. The phase opposite to El Niño is La Niña. In that case, the trade winds do not weaken but become stronger than usual, pushing the warm surface water even farther west across the Pacific, while cold water in the eastern Pacific rises more vigorously. The atmosphere is forced to adjust to that change, and weather patterns often shift in the opposite direction of what is typically observed during El Niño. That is why some regions that are usually dry may face flooding, while areas that normally receive frequent rainfall may fall into drought when the ocean atmosphere system shifts its state. National Oceanic and Atmospheric Administration monitors ENSO using a network of buoys, satellites, and ocean temperature measurements. Changes in sea surface temperature in the equatorial Pacific alone can influence hurricane activity in the Atlantic, the strength of the Asian monsoon, and the paths of winter storms across North America. What matters here is that the ocean is not influenced by the atmosphere in only one direction. Feedback loops exist between them. Warmer ocean water increases evaporation. Stronger evaporation adds more water vapor to the atmosphere. Increased water vapor encourages convection and releases more latent heat. That heat can then alter wind patterns, and the winds in turn affect surface currents and upwelling. The entire system remains interconnected and constantly in motion. Not only the surface layer of water matters. Deeper in the ocean, there is also a very slow circulation with global reach, thermohaline circulation. As the name suggests, it is driven by differences in temperature and salinity. Cold water is denser than warm water, and salty water is denser than fresh water. In polar regions, particularly in the North Atlantic, surface water cools strongly and becomes saltier when sea ice forms and expels salt from the ice crystals. When this water becomes dense enough, it sinks and begins a long journey through the deep ocean. This process helps drive what is sometimes called the global conveyor belt, a deep current system that transports water around the planet on timescales ranging from hundreds to thousands of years. Compared with winds in the atmosphere, thermohaline circulation moves much more slowly, yet it remains one of the major mechanisms distributing heat across Earth. Gulf Stream is a well-known example. It carries warm water from the tropics toward the North Atlantic, helping make winters in parts of Western Europe considerably milder than in other places at the same latitude. And when ocean circulation changes, the atmosphere above it can change as well. Sea surface temperatures in key regions shift, pressure systems above them adjust, storm tracks change, and rainfall patterns shift accordingly. Between the ocean and the atmosphere there is constant exchange. Sunlight warms the sea surface. The ocean returns heat to the atmosphere through evaporation, conduction, and radiation. Winds drive surface currents. Currents redistribute heat. Heat influences pressure. Pressure then changes how winds behave. It is a tightly coupled system. Even short-term weather events carry the imprint of ocean conditions. A tropical cyclone can intensify very rapidly over warm water because evaporation continuously pumps latent heat into the storm's core. But if it moves over colder water, its intensity usually weakens. Sometimes the temperature of only the upper few dozen meters of ocean water can determine whether a storm strengthens or fades. Similarly, prolonged heat waves over land can also be linked to long-lasting ocean temperature anomalies that shift atmospheric circulation patterns. The ocean moves on a different timescale from the atmosphere. It changes more slowly, with heat content evolving over weeks, months, or even years. That slow pace gives it a kind of memory. What happens in the ocean today may influence the behavior of the atmosphere months later. For that reason, weather is not written only in the sky. It is also shaped by what lies beneath the sea surface. The waves on the surface of the ocean may appear calm and regular, but beneath them enormous masses of water are storing energy delivered by sunlight. That energy affects evaporation rates, atmospheric moisture, and storm development. The boundary between sea and sky is therefore not a dividing line. It is a zone of continuous exchange of heat, moisture, and momentum. To understand weather, it is not enough to look upward. One must also look downward. The sky responds to the ocean, and the ocean responds to the sky. Together they form a coupled system, from local sea breeze circulations to global oscillations such as ENSO, and within that relationship, an important distinction begins to appear: the difference between short-term atmospheric variability and the long-term patterns that shape a region's expectations. In other words, this is where the relationship between everyday weather and climate becomes clearer. A cold morning, a sudden downpour, a week of beautiful sunshine. These are experiences of weather. They are immediate, local, and often brief. Weather is the short-term state of the atmosphere at a specific place and time. Temperature, wind speed and direction, humidity, cloud cover, precipitation, and pressure. It changes constantly. A single frontal passage can alter conditions within a few hours. A thunderstorm can transform the entire sky in just minutes. Even the calmest day is never truly still. Subtle variations continue from sunrise to sunset. Climate is something different. It does not describe a single hot day or a snowy afternoon. Climate is the long-term statistical picture of weather patterns in a region. It describes averages, variability, and trends derived from many decades of data. By convention, climatologists often use a period of about 30 years to define climate normals, because that span is long enough to smooth out short-term fluctuations and reveal typical conditions. If weather describes what is happening today, climate describes what tends to happen over many years. A city may be described as having mild winters and warm summers. That does not mean every winter day is mild or every summer day equally warm. It simply means that when averaged over many decades, that pattern emerges clearly. Individual weather events can still deviate far from the average without immediately changing the climate of that place. The study of those long-term patterns belongs to climatology. This field examines temperature records, precipitation patterns, circulation trends, and the interactions between the atmosphere, ocean, land, and ice. Its goal is to understand not only natural variability, but also long-term changes in Earth's energy balance. Organizations such as the Intergovernmental Panel on Climate Change evaluate the broader landscape of climate research. They do not conduct the original experiments themselves, but synthesize and assess results from thousands of scientific studies worldwide, drawing on contributions from meteorologists, oceanographers, physicists, and many other disciplines. To properly understand the relationship between weather and climate, the key point is distinguishing variability from trends. Variability refers to natural fluctuations that can last from days to years. A strong El Niño may bring unusually warm winters to one region and heavy rainfall to another. A volcanic eruption may temporarily cool global temperatures by injecting reflective particles into the stratosphere. These are fluctuations within the climate system. A trend is different. It is a sustained change in average conditions over a long period. When global average temperatures rise steadily over many decades, that is no longer a short-term fluctuation. It is a trend. Confusion often begins when a single weather event is used to draw conclusions about long-term climate. A cold winter by itself does not disprove a warming trend. A single heat wave is not enough to define a climate. Climate does not reside in a single day. It emerges from the accumulation of countless days over time. There is a helpful way to imagine this. Think of a rolling landscape. Weather is like the waves rising and falling across its surface. Climate is the shape of the terrain beneath. The waves can change quickly, but the underlying landscape changes much more slowly, and climate sets the broad boundaries within which weather takes place. Climate sets the broad framework within which daily weather unfolds. In a polar climate, even warmer summer days are still cold compared with the tropics. In a desert climate, rain is rare, so even though storms may still occur from time to time, the system's everyday possibilities are limited by its average state. What creates that framework is far from simple. The temperature contrast between the equator and the poles, the way the oceans distribute heat, the composition of the atmosphere, and the planet's albedo all help define climate. From those factors arise the large circulation patterns such as the Hadley cells and the jet streams, and those same patterns then work downward to influence the weather of each day. Climatology, therefore, does not merely observe temperature or rainfall. It also tracks slower feedbacks, the ones operating in the background of the system over long periods of time. Changes in sea ice can alter albedo, which then changes the amount of solar radiation being absorbed. Changes in vegetation can alter both the reflectivity of the surface and the exchange of moisture with the air. Changes in greenhouse gas concentrations can shift the balance between incoming radiation and outgoing infrared radiation. Climate, in its fullest sense, is the integrated result of what happens in the atmosphere, the ocean, the cryosphere, and the biosphere. Weather forecasting and climate science therefore stand on the same physical foundation, but they answer different questions. Weather forecasting tries to estimate what the sky will do over the next few days or weeks. Climate science is concerned with the average behavior of the system over many decades or longer. Both rely on thermodynamics and fluid dynamics, but one focuses on short-term expressions, while the other examines accumulated patterns. That is why, even though the atmosphere can be very difficult to predict on short timescales because of its chaotic nature, long-term statistical patterns still remain meaningful. We may never be able to say with certainty exactly what time it will rain on a given day many years from now, but we can still estimate the average conditions of an entire season based on climate patterns and historical data. The difference between weather and climate is not just a matter of wording. It helps us understand the atmosphere on different timescales. Weather is the immediate expression. Climate is the pattern that has settled over time. When a weather report says that today is warmer than average, it is placing short-term weather beside long-term climate normals. When climate scientists review decades of temperature data, they are asking whether those normals themselves are shifting. Both perspectives are necessary. Without weather, climate becomes too abstract an idea. Without climate, weather seems like scattered fragments with no context. While individual storms form and fade, and fronts advance and retreat, the averages in the background are still quietly accumulating, revealing patterns that no single event could ever show on its own. Once that distinction is clear, another question arises almost naturally. How far ahead can we predict the behavior of the atmosphere? And what truly limits that prediction? There are mornings when the forecast seems astonishingly accurate. Rain arrives at almost exactly the predicted time. The temperature matches the forecast closely. But there are also times when sunshine is promised and the clouds linger anyway, or when a storm intensifies beyond what seemed reasonable. The atmosphere follows physics with great precision, yet long-range certainty always slips away from us. The reason lies in a deeper underlying property: chaos. In the early 1960s, Edward Lorenz, a meteorologist working at MIT, was using simplified mathematical models to simulate atmospheric convection. He built systems of equations describing fluid motion and heat transfer, then let a computer evolve them over time. In one experiment, he reran an earlier simulation but entered the initial values with only slightly different rounding than before. Lorenz assumed the new result would be nearly identical to the old one, but it was not. Over time, the two simulations began to diverge dramatically. What he uncovered became one of the most famous ideas in modern science: sensitive dependence on initial conditions. In nonlinear systems such as the atmosphere, tiny differences at the beginning can grow into very different outcomes later on. That does not mean the atmosphere is random. It simply means that small errors in the initial measurements can be amplified as time passes. Two atmospheric states that are almost identical, if allowed to evolve under the same physical laws, can still follow different paths after a few days or weeks. Lorenz used a now famous image to express this idea. Could the flap of a butterfly's wings in Brazil contribute to a tornado in Texas? From that came the butterfly effect. The point is not that butterflies regularly create storms, but that very small disturbances can in principle influence large outcomes in a chaotic system. From this, it becomes clear why weather forecasting depends critically on how accurately we know the current state of the atmosphere. Meteorologists must gather data from weather stations, ocean buoys, radar, satellites, and weather balloons. From these sources, they obtain temperature, pressure, humidity, and wind information at thousands of observation points. But the atmosphere is vast, and measurement is never perfect. Data is denser in places where many people live, and sparser over remote oceans or polar regions. Instruments always have some error, and the atmosphere itself continues to change between one observation and the next. All of those observations are then fed into numerical weather prediction models. These models are built from the fundamental equations of fluid dynamics and thermodynamics, describing how pressure, temperature, wind, and moisture change over time. At the center remain the Navier-Stokes equations, together with the equations for conservation of energy and continuity of mass. Mathematically, they may appear compact, but to solve them for the entire planet, scientists must divide the atmosphere into an enormous three-dimensional grid and perform calculations at every point. The finer the grid, the more detail the model can see. But in exchange, the computational demand rises sharply. That is why centers such as the European Center for Medium-Range Weather Forecasts must run world-leading supercomputers, carrying out trillions of calculations per second to push the state of the atmosphere forward into the future. Even so, uncertainty grows with time. That is why meteorologists do not run just a single model. They use ensemble forecasting. Many simulations run with slightly different initial conditions. Each run opens a different possible future. By comparing the full range of results, they do not ask only what will happen, but also what is the probability of each possibility. If most members of the ensemble show rain on the same day, confidence is higher. If the scenarios spread far apart, uncertainty increases as well. The chaotic nature of the atmosphere, therefore, imposes a practical limit on deterministic forecasting. After about 1 to 2 weeks, the very small errors in the initial conditions have usually grown large enough that day-to-day weather forecasts lose the reliability people need. That limit does not exist because the physics is wrong, nor because humans do not understand the atmosphere well enough. It is an intrinsic property of the system itself. One way to imagine this is to picture two air masses that are almost identical in temperature and position. A tiny difference in their path may cause one to enter a region of rising motion while the other remains in a stable environment. From there, cloud formation changes, pressure changes, the wind field changes, and the effects continue spreading into nearby regions. The system does not lose memory of its initial state all at once, but over time it gradually loses detailed memory as those small initial differences are amplified. Even so, forecasting skill has advanced tremendously over recent decades. Better satellites, more sophisticated data assimilation techniques, and stronger supercomputers have all helped. What once could be forecast reliably only 2 or 3 days ahead can now often be extended to a week or more. Throughout that progress, data assimilation has been an especially critical link. It is the process of combining observational data with model output to create the best possible picture of the current state of the atmosphere, the starting point from which every future forecast must begin. Even as models grow increasingly sophisticated, one fundamental limit does not change. Weather forecasting is not limited because the atmosphere is mysterious or impossible to understand. It is limited because the atmosphere is a non-linear and highly sensitive system. Supercomputing centers continually increase model resolution and improve the parameterization of processes such as cloud formation, radiation transfer, and turbulence. Observations are also incorporated into models selectively, weighted by their reliability before being integrated into the computational framework. Yet all of these efforts cannot erase a basic truth. There is a profound difference between deterministic prediction and statistical prediction. The precise state of the atmosphere weeks from now often lies beyond the limits of detailed forecasting. Broader tendencies, however, such as seasonal temperature anomalies associated with El Niño, are easier to capture because they are tied to slower evolving components of the climate system. Short-term weather, especially convection and storms, is far more sensitive to small errors in the initial conditions. This tension between accuracy and unpredictability defines meteorology itself, a discipline grounded deeply in mathematics, yet inseparable from probability. The physical laws underlying the atmosphere are not vague. Pressure gradients accelerate air. Latent heat release fuels convection. Earth's rotation shapes circulation. Nothing about these principles is uncertain. The uncertainty lies in the specific path the system will follow when countless small variations act on it simultaneously. Understanding this does not diminish the value of forecasting. On the contrary, it clarifies its limits. Why forecasts steadily improve, yet never achieve absolute certainty, and why modern meteorologists rely on probabilities and ensemble forecasts, rather than presenting a single answer, as though the future followed only one path. From a practical perspective, every weather forecast begins with a question that seems simple. What is the atmosphere doing right now? Yet that question is the difficult part. Before computers can push equations into the future, they must have the best possible picture of the present. That picture comes from observations. Around the world, thousands of surface weather stations continuously record temperature, pressure, wind speed, wind direction, and humidity. Some stations operate automatically in remote locations. Others are placed at airports, where precise data is essential for aviation safety. Together they form the foundation of weather forecasting. But the atmosphere is not a flat map. It has depth. What happens at the surface tells only part of the story. For that reason, meteorologists use radio sondes to measure the atmosphere vertically. A radiosonde is a small instrument package attached to a weather balloon filled with helium or hydrogen. Twice each day, at hundreds of locations worldwide, these balloons are released and rise through the troposphere, often reaching the lower stratosphere. As they ascend, they transmit measurements of temperature, pressure, humidity, and wind. From these vertical profiles, scientists can determine how temperature changes with height, where temperature inversions occur, how moist the upper atmosphere is, and how winds vary between layers. These observations are crucial for identifying instability, wind shear, and the potential for storm development. Above all of these direct measurements is the global perspective provided by satellites. Meteorological satellites monitor cloud patterns, sea surface temperatures, atmospheric water vapor, and radiation levels. Some satellites remain in geostationary orbit, appearing nearly fixed above one region of Earth, so they can observe it continuously. Others move in polar orbit, gradually scanning the entire planet. Infrared sensors estimate cloud top temperatures, which reveal cloud height. Visible imagery shows cloud shape and structure during daylight, Microwave sensors can even penetrate many cloud layers to estimate atmospheric moisture and precipitation intensity. Doppler radar provides yet another perspective. It emits pulses of microwave energy and then receives the reflected signal from raindrops or snowflakes in the atmosphere. From the time it takes for the signal to return, meteorologists can determine the location and intensity of precipitation. Using the Doppler effect, radar can also detect whether those particles are moving toward or away from the instrument, revealing the wind structure within storms. The ability to detect rotation inside thunderstorms has dramatically improved tornado warning capabilities. All of this information then flows into forecasting centers around the world, coordinated through international cooperation. Weather does not stop at national borders, and neither can the data used to predict it. Once observations are collected, they do not enter models mechanically. They pass through a critical step called data assimilation. This process combines real observations with a previous model forecast to produce the best possible estimate of the current atmospheric state, what meteorologists call the analysis. From this starting point, the model equations are integrated forward in time. Because the atmosphere is chaotic, forecasters do not rely on a single model run. Instead, they create an ensemble of simulations, with each member beginning from slightly different initial conditions or using slightly different model parameters. These small differences reflect two main sources of uncertainty: errors in observations and limitations in how models represent physical processes. As the ensemble members evolve into the future, they gradually diverge. That divergence reveals the confidence of the forecast. If nearly every ensemble member predicts heavy rain over a region, the probability of that outcome is high. If half predict rain and half predict dry weather, uncertainty is much greater. This is why modern forecasts are often expressed in probabilities. A number such as a 60% chance of rain is not a sign of hesitation. It is a way of translating physical uncertainty into practical information. Tools such as hurricane track spaghetti plots follow the same logic. The closer the paths cluster together, the greater the confidence. The more widely they spread, the greater the uncertainty. Even so, technological progress cannot make forecasting perfect. Observational coverage remains incomplete, especially over oceans and polar regions. Many small-scale processes, such as cloud microphysics and turbulence, must still be approximated through parameterization, rather than solved directly. And although today's computing power is immense, it is still finite. The finer the model grid, the faster computational costs increase. Forecast centers must therefore constantly balance resolution with feasibility. Combined with the atmosphere's sensitive dependence on initial conditions, even very small observational errors can grow over time. Yet over the span of several decades, forecasting skill has clearly improved. A 5-day forecast today is often as accurate as a 2- or 3-day forecast was in the late 20th century. Advances in satellites, data assimilation techniques, and supercomputing have significantly extended the window of reliable prediction. Perhaps the best way to understand forecasting is this: it is not the art of eliminating uncertainty, it is the process of reducing uncertainty as much as possible, and then communicating the remaining uncertainty clearly and usefully. When someone opens a phone app to check the forecast or listens to a weather report on the radio, what they receive is the final result of millions of measurements, extraordinarily complex mathematical simulations, and a continuous network of international scientific cooperation working behind the scenes. A small sun or cloud icon on a phone screen looks so simple that it is easy to forget the entire world of physics, computational modeling, and international cooperation behind it. Weather forecasting is not merely a convenience. It connects atmospheric science with everyday life, influencing how people make decisions about travel, agriculture, emergency response, and even ordinary leisure plans. It helps communities prepare for potential risks, while always acknowledging that the chaotic nature of the atmosphere will preserve some degree of uncertainty that can never disappear completely. The sky may never be forecast with perfect accuracy, yet each advance in observation and modeling sharpens human understanding. especially when weather shifts toward unusual or violent states, when the timing of warnings and the assessment of probabilities become most critical. Most days, the atmosphere speaks in a relatively gentle voice. A breeze moves across a field, rain falls steadily, clouds arrive and depart without urgency. But the same physical system can also produce the most extreme events. Extremes are not governed by a different set of natural laws. They simply occur when the atmosphere operates near the limits of the energy it can access. Consider tornadoes. A tornado is a rapidly rotating column of air extending from a thunderstorm cloud to the ground. Most tornadoes form within supercells, a type of thunderstorm that develops when strong instability combines with significant vertical wind shear. That wind shear creates conditions in which horizontally rotating tubes of air can develop in the lower atmosphere. If a sufficiently strong updraft tilts that horizontal rotation into a vertical orientation, a mesocyclone may form a rotating core within the updraft. Inside a mesocyclone, pressure can continue to fall as air converges and stretches upward. The rotation can intensify further through the conservation of angular momentum. If that rotating column tightens and extends downward, a tornado may form. Yet not every supercell produces a tornado. Adequate moisture, instability, and wind shear are not always sufficient. The conditions must align in a very delicate way. That is why two storms may appear almost identical on radar, yet only one produces a tornado. Doppler radar observations have greatly improved warning capability by detecting rotation within storms before a tornado reaches the ground, and research by the National Weather Service and the Storm Prediction Center has clarified many of these processes. Even so, tornado formation remains one of the most sensitive phenomena in the atmosphere. In another form of extreme weather, the danger does not come from localized rotation but from the large-scale transport of moisture. Atmospheric rivers are long, narrow corridors of concentrated water vapor carried by strong low-level winds from the tropics or subtropics toward the mid-latitudes. When these moisture-rich flows encounter mountain ranges or frontal systems, the water vapor is forced to condense, and heavy rain or snow begins to fall. The term atmospheric river is not accidental. On satellite images, they truly resemble rivers flowing through the sky. A strong event can transport more water vapor than the average discharge at the mouth of the Amazon River. Along the west coast of North America, atmospheric rivers are both a valuable source of water for reservoirs and winter snowpack, and a potential cause of flooding when they persist or repeatedly strike the same region. Temperature extremes also arise from specific mechanisms within the same physical framework. Heat waves develop when a high-pressure system or upper-level ridge remains in place long enough. Air beneath that ridge sinks, compresses, and warms. Clear skies allow the surface to absorb more sunlight. If this pattern persists for many days or weeks, temperatures can rise far above average. At the same time, fewer clouds reduce evaporative cooling. Soil moisture declines, weakening latent heat flux and leaving more energy available to heat the surface. The land therefore warms more quickly, reinforcing the high-pressure pattern. Heat waves strengthen through feedback processes such as these. In the opposite direction are severe cold outbreaks, often associated with deep troughs in the jet stream. When the jet stream plunges sharply southward, extremely cold polar air can spill far toward the equator and invade regions that are usually more temperate. Behind the cold front, surface high pressure can produce clear skies, allowing heat to radiate rapidly into space at night and causing temperatures to drop further. Both heat waves and cold spells illustrate the same principle. When circulation patterns become amplified, weather can be pushed into states far more extreme than usual. Blocking patterns, which occur when Rossby waves grow large and slow down, can trap hot air in one region and cold air in another for extended periods. Most severe weather events arise from several factors aligning at once. A strong temperature gradient, abundant moisture, sustained upper-level support, and favorable wind shear may combine to produce a major event. The atmosphere is not always in equilibrium. It is constantly redistributing energy, and sometimes that redistribution occurs rapidly and violently. The National Weather Service studies these states to improve warnings and preparedness. Statistical analyses of past severe storms, major floods, or heat waves combined with improved modeling help scientists identify patterns that precede large extreme events. It is important to recognize that extremes are a natural part of atmospheric variability. Historical records of powerful storms, droughts, and harsh winters extend far back in time. What changes over time is not whether extremes exist, but the background climate in which they occur. A heat wave occurring in a warmer climate will reach higher absolute temperatures than a similar heat wave in a cooler climate. Likewise, changes in sea surface temperature can intensify extreme rainfall. Extremes therefore reveal the full range of atmospheric behavior. Tornadoes compress rotational energy into a narrow column. Atmospheric rivers represent large-scale moisture transport. Heat waves reflect persistent upper-level ridges, and cold outbreaks arise from rapid southward surges of polar air. They differ in scale and impact, but all follow the same physical principles that govern both calm, sunny days and gentle rain. The atmosphere does not switch to a different set of rules when weather becomes violent. It continues to obey thermodynamics, fluid dynamics, and conservation laws. What changes in extreme conditions is the magnitude and alignment of the forces driving the system. To understand such phenomena, the atmosphere must be viewed as a connected system, where short-term disturbances and planetary scale patterns influence one another simultaneously. And when one looks beyond individual events, longer processes can be seen shaping the frequency, intensity, and location of extremes across decades or centuries. This is where the concept of feedback becomes very important. The atmosphere does not simply respond to external changes, it often responds to its own responses. A feedback loop occurs when a process within the system acts back upon itself, either strengthening or weakening the original change. For that reason, two basic types of feedback exist: positive and negative. Positive feedback amplifies an initial change. If a warming trend triggers mechanisms that produce additional warming, that is positive feedback. Negative feedback does the opposite. It reduces the original effect. The words positive and negative here do not mean good or bad. They simply describe the direction of influence. One of the most important atmospheric feedbacks involves water vapor itself. Water vapor is the most abundant greenhouse gas in Earth's atmosphere. It absorbs and emits infrared radiation, trapping part of the heat that would otherwise escape into space. The crucial point is that warmer air can hold more water vapor. This relationship is described by the Clausius-Clapeyron equation, in which saturation vapor pressure rises rapidly with increasing temperature. As a result, if the atmosphere warms even slightly because of an external influence such as higher greenhouse gas concentrations or increased solar radiation, it gains the capacity to hold more water vapor. As air warms and can hold more water vapor, the story does not end with humidity. That additional vapor continues to absorb and re-emit infrared radiation in the atmosphere, strengthening the greenhouse effect and driving temperatures even higher. That is the water vapor feedback, a positive feedback. The important point here is that the initial warming is not triggered by water vapor itself. It begins with another forcing, and water vapor enters afterward as an amplifier. This is one of the strongest amplifying mechanisms in the climate system, consistently shown in modeling studies, and satellite observations also indicate that atmospheric moisture has generally increased in a warming atmosphere, just as thermodynamics had long suggested. But while water vapor feedback appears fairly direct, cloud feedback is much more complicated. Clouds affect Earth's energy balance in two nearly opposite ways. Low, thick clouds strongly reflect incoming solar radiation, increasing the planet's albedo and contributing to cooling. By contrast, high, thin clouds tend to trap outgoing infrared radiation, thereby contributing to warming. So if a warmer climate leads to more reflective low clouds, that would be a negative feedback. If it leads to more heat-trapping high clouds, that would be a positive feedback. The problem is that the atmosphere does not distribute clouds according to such simple rules. The greatest difficulty lies in predicting how clouds will change, where they will appear, at what altitude, whether they will thicken or thin, and whether they will cover more or less of the sky. Cloud microphysics operates on scales far smaller than what global climate models can directly resolve. The formation of droplets, the growth of ice crystals, and turbulent motion within clouds all affect the final properties of clouds. For that reason, modern models must use parameterization to represent these processes that are too small to simulate directly. Centers such as NCAR and ECMWF continuously refine these representations, but cloud feedback remains one of the largest sources of uncertainty in climate projections. Some observations suggest that certain types of low clouds may decrease slightly in some regions as the climate warms, which could amplify warming. But other studies indicate that regional differences are so complex that they cannot be reduced to a single conclusion. Feedbacks in the atmosphere also never operate in isolation. They overlap, interact, and sometimes partly cancel one another. Consider sea ice feedback. As the polar regions warm, sea ice melts. Ice reflects sunlight strongly, while open ocean water is darker and absorbs much more solar energy. So the more ice melts, the more ocean is exposed, the more heat is absorbed, and the more ice melts further. This is a very clear, positive feedback, but at the same time, a warmer ocean may increase evaporation, and in some places that could lead to more cloud cover, which may partly limit local warming. It is this kind of layered interaction that makes the atmosphere's response nonlinear. Nonlinear here means that the system does not respond in a simple one-to-one proportion to the initial change. A small forcing can produce a much larger consequence if the right amplifying feedbacks are present. Conversely, sufficiently strong negative feedbacks can make the system less sensitive and more stable. This is a defining feature of atmospheric dynamics, and it also explains why thresholds matter so much. Surface temperature only has to pass a certain range for circulation patterns to change. Humidity only has to reach a certain level for convection to intensify rapidly. Climate models therefore must try to simulate not just radiation or moisture transport separately, but the way radiation, convection, humidity, and surface processes continuously influence one another over time. Only by running many simulations under different conditions can scientists evaluate how feedbacks shape long-term outcomes, and it is exactly this kind of research that the IPCC assesses when evaluating the confidence of projected changes. Although some uncertainties remain, especially around clouds and regionally specific feedbacks, major mechanisms such as water vapor feedback and ice albedo feedback are supported by very strong evidence. And feedback does not exist only on the scale of global climate. In a growing thunderstorm, latent heat release strengthens the updraft, and the stronger updraft leads to more condensation, a positive feedback on a local scale. Later, when downdrafts develop and cut off the supply of warm air feeding the storm, that becomes a negative feedback. So from a single cloud to the entire planetary circulation, the atmosphere is always a system of interwoven feedbacks. Understanding feedback helps explain why some changes do not stop on their own but instead intensify, why gradual warming can produce amplified temperature increases in the polar regions, and why humidity tends to respond in a fairly predictable way to changes in temperature. But at the same time, feedback reminds us that the atmosphere does not behave in a straight line. One influence can branch into many pathways. One process can be weakened or strengthened by another. The sky may look calm, but beneath that calm lies an entire network of mechanisms continuously adjusting to maintain energy balance. Within that network, chemistry plays a role that cannot be overlooked. The atmosphere is not only a moving fluid, but also a reactive chemical mixture. Nitrogen and oxygen make up most of the air, but gases present only in small amounts can still have enormous effects on radiation, temperature, structure, and the way energy is retained or released. One of the clearest examples lies in the stratosphere, where temperature does not decrease with altitude as it does in the troposphere, but instead increases. The reason lies in ozone, The ozone layer is concentrated mainly between about 15 and 35 kilometers above Earth's surface. Ozone is a molecule made of 3 oxygen atoms. It forms when ultraviolet radiation from the sun breaks apart a normal oxygen molecule, which has only 2 atoms, into free oxygen atoms. These atoms can then combine with other oxygen molecules to form ozone. This is a classic photochemical process, a chemical reaction initiated by light, in this case high-energy ultraviolet radiation. Ozone then strongly absorbs a significant portion of the incoming ultraviolet radiation, especially UVB and UVC. By absorbing it, ozone converts light energy into heat, warming the surrounding air and creating the characteristic temperature inversion of the stratosphere. Without the ozone layer, the amount of ultraviolet radiation reaching the surface would be far greater and would pose extremely serious biological risks. In that sense, ozone acts as a protective shield. But in the late 20th century, scientists discovered that this shield was being significantly eroded over Antarctica during the Southern Hemisphere spring. The work of atmospheric chemists such as Mario Molina and F. Sherwood Rowland showed that the main cause was CFCs, compounds once widely used in refrigeration systems and aerosol sprays. When these compounds reached the stratosphere and were broken down by ultraviolet radiation, they released chlorine atoms. A single chlorine atom could then catalytically destroy thousands of ozone molecules through repeated cycles. In the cold polar stratosphere, these reactions became even more effective because of the presence of polar stratospheric clouds, which provided favorable conditions for activating chlorine. In response to this scientific evidence, the Montreal Protocol was adopted in 1987, with an international commitment to phase out ozone-depleting substances. This treaty is often regarded as one of the greatest successes of global environmental cooperation, and observations today show that stratospheric ozone is gradually recovering, although the full recovery process will still take many more decades. The example of ozone clearly shows that atmospheric chemistry is not a minor detail. It can directly shape both the temperature structure and the radiation balance of the sky. In the lower atmosphere, greenhouse gases play a different role, but one that is no less profound. Carbon dioxide, methane, nitrous oxide, water vapor, and even ozone in the troposphere all participate in a fundamental process. They absorb infrared radiation emitted by Earth's surface and then re-emit it in many directions, including back toward the ground. Because of this, heat does not escape to space too quickly, and the surface of the planet maintains temperatures far warmer than it would without this mechanism. The greenhouse effect, in that sense, is not an abnormal phenomenon. It is a natural and essential component of the climate system. Without it, the average surface temperature would be much lower, and liquid water would be so rare that sustaining the world we know would be difficult. What is striking is that large effects can sometimes come from components present in very small amounts. Carbon dioxide exists at only a few hundred parts per million, yet it carries significant weight in the planet's energy balance because it absorbs infrared radiation at specific wavelengths. Methane is even less abundant, but over shorter time periods each molecule traps heat more efficiently. The interaction between these gases and radiation helps shape the vertical temperature profile of the atmosphere. In the troposphere, they warm the system from below, but in the stratosphere, increasing greenhouse gas concentrations can actually lead to cooling, because less infrared radiation from below reaches those higher altitudes. This difference shows that chemistry and radiation do not influence the atmosphere uniformly everywhere. Their effects vary with atmospheric layers. Photochemistry is not limited to the stratosphere either. In the troposphere, urban air pollution can produce ground-level ozone through reactions between nitrogen oxides, volatile organic compounds, and sunlight. Unlike stratospheric ozone, which protects life by filtering ultraviolet radiation, tropospheric ozone can harm human respiration and plant life. This reminds us that atmospheric chemistry is not confined to a single layer. It extends throughout the entire column of air, continuously shaped by light, temperature, and human activity. Modern climate models, therefore, cannot simulate only wind, clouds, and temperature. They must also incorporate detailed chemical processes, photochemical reactions, emission sources, the transport of substances through the atmosphere, and removal mechanisms such as deposition or chemical breakdown. Chemistry does not only alter temperature, it also affects clouds. Aerosol particles, sometimes originating from volcanoes, sea salt, or desert dust, and sometimes from industrial activity, act as condensation nuclei. Even small changes in their concentration can alter the size of cloud droplets and the reflectivity of clouds, which in turn affects the albedo of the entire system. In that sense, the sky has never been a chemically static environment. Ultraviolet radiation constantly creates and destroys ozone. Infrared radiation continuously interacts with greenhouse gases to regulate temperature. Compounds introduced by human activity can shift these balances. As the story of CFCs once demonstrated, physical motion and chemical composition therefore cannot be separated. Rising air can carry chemical compounds upward. Stratospheric circulation redistributes ozone. Emissions from the surface are transported across continents and oceans by wind. To understand weather fully, one must accept that beyond pressure, temperature, and humidity, there is also a chemical dimension quietly determining how radiation is absorbed and emitted, thereby reshaping the temperature gradients on which convection and circulation depend. The atmosphere is both a fluid and a chemical reactor. If we step back even further from individual clouds, fronts, and storms, a broader picture begins to emerge. The atmosphere is not a collection of isolated pieces, it is a system. In the language of environmental science, a system consists of components, connected by relationships, continuously exchanging matter and energy. The atmosphere fits this definition almost perfectly. It exchanges heat with the surface, moisture with the oceans, momentum with Earth's rotation, and radiation with space. In such a structure, no process truly exists in isolation. Convection interacts with radiation. Chemistry modifies temperature gradients. Ocean currents reshape pressure fields. Every component influences the others. One of the most elegant ideas in systems theory is emergence. Complex patterns can arise from countless simple interactions between smaller elements. No air molecule decides to create a storm. No water droplet intends to join a spiraling cloud band. Yet when billions of these small interactions follow consistent physical laws, large structures begin to appear. A hurricane, for instance, emerges from the combined effects of warm ocean water, rising moist air, pressure gradients, and planetary rotation. Each step individually follows ordinary thermodynamics and fluid dynamics, but together they form a rotating system hundreds of kilometers wide. The Hadley, Ferrel, and polar cells operate in a similar way. Each parcel of air responds locally to temperature and pressure differences, but taken together, they organize themselves into hemisphere-scale circulation patterns. The connection from the local to the global is a fundamental property of the atmosphere. A bubble of warm air rising, cooling, and forming a cloud is a small-scale event. Thousands of such updrafts combined can begin to influence regional pressure fields. On planetary scales, the energy imbalance between the equator and the poles generates circulation belts and jet streams. At the same time, the atmosphere operates across an enormous range of timescales. Disturbances measured in meters influence cloud microphysics. Synoptic systems spanning thousands of kilometers shape continental weather, and climate oscillations unfold across years or decades. No single scientific discipline is enough to capture the entire picture. Physics, chemistry, mathematics, oceanography, and computer science all play essential roles. Centers such as NCAR, ECMWF, and research groups at universities around the world work with coupled models in which atmospheric dynamics are linked with ocean circulation, land surface processes, and chemical cycles. These models treat the atmosphere as a complex adaptive system, where a disturbance in one component can propagate through many others. Amid all this motion, one theme appears again and again: balance. The atmosphere constantly seeks balance in response to energy imbalances, yet it rarely reaches a truly static state. Instead, it lives in dynamic equilibrium. Warm air rises and cools. Cold air sinks and warms. Water evaporates and then condenses. Radiation enters and then escapes back to space. And within this constant change, order still appears. Jet streams maintain recognizable corridors. Circulation cells preserve familiar structures, and seasons repeat with a rhythm that is easy to recognize. Chaos at small scales coexists with organization at large scales. Perhaps it is precisely this coexistence that defines the character of the atmosphere. Chaos theory explains why the atmosphere is sensitive to initial conditions. Systems theory explains why organized structures can still emerge within that sensitivity. A snowflake offers a beautiful example. Each crystal grows from molecular interactions between water vapor and ice surfaces, with temperature and humidity shaping its branching patterns. From those microscopic rules emerges a delicate, symmetrical form. On vastly larger scales, planetary waves bending through the jet stream also emerge from basic principles such as conservation of angular momentum and temperature gradients. The scales differ enormously, but the underlying logic is similar. Self-organization does not mean that some invisible hand controls every detail. It simply means that when energy flows through a sufficiently complex system, patterns can form spontaneously from internal interactions. In the atmosphere, solar radiation enters as energy input. Infrared radiation leaving to space acts as energy output. And between those flows, motion and chemistry continually rearrange energy across space and time. Positive feedback can accelerate a developing system, such as intensified convection in a tropical cyclone. Negative feedback can reduce extremes, such as radiative cooling, helping balance the surface after sunset. The atmosphere is therefore neither completely random nor rigidly fixed. It fluctuates within boundaries defined by physical laws and boundary conditions. Even extreme events remain inside this framework. Tornadoes arise from instability and wind shear. Atmospheric rivers result from concentrated moisture transport along circulation pathways. They are not strange exceptions to the system, but rather some of the most powerful expressions of the dynamic potential that the system always contains. Viewing the atmosphere as a self-organizing system forces us to stop separating wind from moisture or heat from chemistry as if they were independent chapters. Energy drives motion. Motion redistributes heat and moisture. Chemistry alters radiation. Radiation changes temperature gradients. Temperature gradients then reshape motion again. The processes connect continuously in this way. And so, on a quiet evening when clouds drift slowly and the wind softens, the atmosphere may appear to be resting. In reality, it continues adjusting itself on scales too large or too subtle for the eye to notice immediately. From water molecules quietly gathering into droplets to the broad arc of a jet stream sweeping across a hemisphere, the sky continues organizing itself through simple rules repeated across countless scales. The result is a living tapestry of motion and balance, intricate, complex, yet always grounded in consistent principles. When all the pieces are seen together, wind, rain, storms, heat waves, clouds, chemical reactions, jet streams, oceans, the picture can easily feel overwhelming. There are bands of wind stretching across hemispheres, microscopic droplets forming around aerosols, rotating storms drawing heat from tropical seas, and chemical reactions unfolding silently in the stratosphere. It is easy to see weather as an endless list of different phenomena, but if all of it were compressed into a single idea, it might be this. Weather, in the end, is the redistribution of energy through the air. If the entire vast picture had to be condensed into a single idea, it might be this. Weather is energy moving through the air. Everything begins with sunlight arriving from the sun, a star nearly 150 million kilometers from Earth. Yet that flow of energy does not fall evenly across the planet's surface. The equator receives more than the poles. Land responds differently than the oceans. Dark surfaces retain more heat than bright ones. Energy therefore starts out unevenly distributed. And each of those differences is, in essence, a small imbalance waiting to be resolved. The atmosphere responds to that imbalance with motion. That is where weather truly begins. Where it is warmer, air expands, becomes less dense, and tends to rise. Where it is colder, air contracts, becomes denser, and tends to sink. The ideal gas law ties these changes together through a tight relationship between temperature, pressure, and density. Even a small change in temperature shifts the balance. Convection emerges from that shift. Air rises, air sinks, and a circulation begins to form, as if the atmosphere were searching for a pathway to smooth out the difference. But air does not move on a motionless planet. Earth rotates, and that rotation bends the winds that begin to form. The Coriolis effect does not create motion on its own, but it organizes that motion into larger patterns: the trade winds, the mid-latitude westerlies, and the polar easterlies. From these wind paths, circulation cells emerge. The Hadley cell carries energy away from the equator. The ferrule and polar cells continue that transport toward higher latitudes. Higher in the atmosphere, jet streams cut across the upper troposphere like fast-moving rivers of air, guiding storms and linking temperature contrasts in one region with weather in another. If the atmosphere contained only dry air, it would already be capable of producing motion. But water intensifies everything. When water evaporates from a warm ocean, energy absorbed from sunlight becomes hidden within water vapor as latent heat. When that vapor condenses higher in the atmosphere, the stored energy returns to the air and strengthens rising currents. A phase change that appears quite ordinary from liquid to vapor and back again can power towering cumulonimbus clouds and tropical cyclones hundreds of kilometers across. At the smallest scale, a speck of dust or a crystal of sea salt may become the first surface upon which a droplet forms. At the largest scale, planetary waves ripple through the jet stream and carry weather across entire continents. From micrometers to thousands of kilometers, the same physical laws are at work. Fluid dynamics explains how air accelerates when forces act upon it. Thermodynamics describes how heat is exchanged and transformed. Radiative transfer explains how energy enters and leaves the atmosphere. Chemistry determines which parts of the radiation spectrum are absorbed or emitted. Systems theory reveals how local interactions can grow into global patterns. Seen this way, even extreme weather no longer appears as an exception. Tornadoes are concentrated expressions of rotation and instability. Atmospheric rivers are organized corridors of moisture transport. Heat waves are signatures of persistent high pressure and sinking air. Each phenomenon represents a way in which the atmosphere redistributes energy under its particular boundary conditions. For that reason, weather never exists separately from the rest of the Earth system. It cannot be separated from climate, because climate sets the average state within which weather occurs. It cannot be separated from the oceans, because the seas store and release heat, shaping atmospheric patterns in return. Nor can it be separated from chemistry, because ozone and greenhouse gases determine how much energy is retained and how much escapes, influencing temperature structure from the very beginning. Every component is connected. What is remarkable is that despite this complexity, the atmosphere does not invent new rules each day. It always follows the conservation of energy, the conservation of mass, and the conservation of momentum. It always responds to imbalance by moving toward a form of dynamic equilibrium. Because that equilibrium is dynamic, the sky can appear both ordered and chaotic at the same time. Circulation cells return with the seasons. Monsoons follow their rhythms. Storm tracks shift but remain guided by upper-level winds. Weather, in this sense, is predictable in its large structures yet elusive in its small details. A breeze touching the skin is not merely a local event. It is part of a circulation linking the equator to the poles. A raindrop falling on a rooftop may not have begun in the cloud overhead, but perhaps from ocean water that evaporated days earlier under sunlight. A cloud forming along a mountainside reveals air forced upward, cooling at the adiabatic lapse rate until condensation begins. Seen this way, weather becomes far less mysterious. It is no longer a collection of isolated events, but a continuous task carried out by the atmosphere, transporting energy from where it is abundant to where it is scarce. The scale of that task is enough to make one pause. A single thunderstorm can release as much energy as many human power plants operating together, yet its origin lies in ordinary sunlight and ordinary water vapor. There is something beautiful in this contrast. The underlying laws are simple, but the patterns they produce are nearly endless in their richness. So, when one looks up at the sky, whether it is clear, filled with clouds, or trembling with thunder, it is possible to see more than changing shapes. One can see a vast self-organizing system in motion, balancing forces, moving heat across the planet, and maintaining the delicate conditions that allow life to exist. The sky is not a motionless backdrop. It inhales sunlight and exhales infrared radiation. It circulates, condenses, and radiates again. It is not magic, nor is it a mystery beyond understanding. It is complexity emerging from simple principles, structure born from motion, imbalance continually seeking balance, again and again. And perhaps that is the best way to hold on to everything that has come before. When clouds gather, when the wind rises, when rain begins, or when the sky is simply calm, the process continues. Energy from the sun is still being redistributed, heat is still moving, water is still cycling, air is still responding to gradients written across the planet. Above us, the atmosphere continues, its familiar work, thin yet powerful, fragile yet dynamic, governed by laws that have operated for billions of years. And within that constant motion, life continues quietly beneath a sky that never truly rests, yet rarely loses its balance.